For decades, the question of whether humanity is alone in the universe lived at the edge of serious science, discussed, considered, but rarely treated as something that might soon be answered. That has changed. The signals are no longer hypothetical. They are recorded, analysed, archived. Some have been explained, others have not, and a growing number of them cannot be dismissed as instrument error, natural phenomena, or human interference. Something is reaching us from the dark, and the institutions that once treated this subject with contempt are now studying it openly. The evidence has been accumulating quietly, until it could no longer be ignored. If you find yourself drawn to the questions that science once refused to ask, consider hitting that like button and subscribing. It genuinely helps this channel continue, and every single one of you matters. Now, let's begin. There is a question that science has spent most of its history trying to either avoid or quietly bury. The question of whether we are alone, not in any narrow biological sense, not whether bacteria might exist beneath the ice of Europa, or whether microbial life might once have crawled across the dry valleys of Mars. The deeper, more disquieting version of the question. The one that asks whether somewhere in this universe of 2 trillion observable galaxies, each containing hundreds of billions of stars, there exists another mind that knows it exists. For most of human history, that question belonged to mythology, religion, and speculation. The idea that intelligent life might exist elsewhere in the cosmos was either a religious heresy, a literary device, or a philosophical exercise. It was not a scientific subject. There was no instrument that could probe it, no methodology that could test it, no framework that could make the question respectable in the eyes of working physicists or astronomers. To take it seriously was to mark oneself as someone unserious. The question was real enough that it kept appearing in human thought, century after century, but it was never quite real enough to deserve a laboratory or a telescope or a research grant. That has changed. Slowly at first, then with accelerating speed over the past 2 decades, the question has migrated from the margins of intellectual life into the centre of several converging fields. Astrobiology now exists as a recognised scientific discipline, taught at major universities, supported by NASA programs and international institutions. The search for biosignatures, chemical traces of life in the atmospheres of distant planets, is being conducted by the most expensive telescope ever launched. The search for technosignatures, evidence of artificial constructions and transmissions from other civilizations, millions of dollars in private and institutional funding. Government agencies that once refused to discuss the subject of unidentified aerial phenomena are now releasing formal reports on it, holding congressional hearings, and establishing official offices to investigate it. None of this happened because the cultural appetite for the subject increased. The cultural appetite for the subject has always been enormous, and that appetite has never been sufficient to overcome the resistance of working scientists who, until recently, regarded the topic as a career-ending distraction. Something changed, something accumulated. Something forced the institutions to take seriously what they had spent generations trying not to discuss. The thing that changed was the evidence, not in the form of any single dramatic discovery that resolved the question once and for all, but in the form of a steady, quiet accumulation of observations that have proven difficult to dismiss. Signals from radio telescopes that match no known natural source. Atmospheric chemistry on distant planets that resembles, in some cases uncomfortably, the chemistry of biology. Interstellar objects whose trajectories and behaviour do not conform to expectations for natural cometary debris. Government records of encounters with objects exhibiting flight characteristics that violate the physics of any known human technology. None of these observations, in isolation, proves anything. Taken together, they have produced a situation in which the scientific community can no longer treat the question of extraterrestrial intelligence as a topic outside the boundaries of legitimate inquiry. The question has refused to stay silent, and the silence that surrounded it for so long has finally broken. The word theory has a specific meaning in science that differs from its everyday use. In ordinary conversation, a theory is something tentative, unproven, perhaps speculative. In science, a theory is a framework supported by enough evidence and explanatory power that it is the working model of how some aspect of reality operates. The theory of evolution, the theory of plate tectonics, the theory of gravity, these are not guesses, they are the structured understandings that organize entire scientific fields. For most of the late 20th century, the existence of extraterrestrial intelligence was not a theory in either sense. It was a hypothesis at best, a possibility that could be discussed but not seriously investigated, supported by no direct evidence and resting almost entirely on probabilistic arguments. The Drake equation, developed by Frank Drake in 1961, provided a framework for estimating how many communicating civilizations might exist in the Milky Way galaxy. But every variable in that equation was, at the time, almost entirely speculative. The fraction of stars with planets, the fraction of planets capable of supporting life, the fraction of life-bearing planets that develop intelligence, the fraction of intelligent species that develop the capacity for interstellar communication. Each was a placeholder for a number that no one knew, and the answers ranged across so many orders of magnitude that the equation could be made to predict anything from a galaxy teeming with civilizations to a galaxy where humanity was the only intelligence. That ambiguity is no longer the situation. Several of Drake's original variables have been constrained dramatically by observation in the past 2 decades. The fraction of stars with planets, once entirely unknown, is now estimated to be near unity. Virtually every star has at least some planets, and the average number per star appears to be substantial. The fraction of those planets in habitable zones, regions where liquid water could exist on the surface, is also better constrained. The Kepler Space Telescope and its successors have identified thousands of exoplanets and demonstrated that Earth-like worlds in habitable orbits are not rare cosmic accidents, but ordinary features of stellar systems. The number of potentially habitable planets in the Milky Way is now estimated, with reasonable confidence, to be in the billions. Simultaneously, the detection capabilities of radio astronomy and optical astronomy have improved by orders of magnitude. Telescopes can now scan large fractions of the sky at multiple frequencies, searching for signals that would have been impossible to detect with the instruments of even 30 years ago. Computational analysis allows the processing of vast datasets in real time, flagging anomalies that would once have remained buried in noise. The infrastructure of the search has been transformed. The instruments are far more sensitive, the data are far more comprehensive, and the analytical tools are far more powerful. This transformation has produced a shift in how the scientific community treats the subject. The question is no longer whether civilizations might theoretically exist. The question is what the observed evidence is telling us about what does exist. Signals are being detected that cannot be casually dismissed. Anomalies are being recorded that resist standard explanations. Patterns are emerging in data that exceed the threshold for serious investigation. The hypothesis has not become a theory in the technical sense. There is no unified framework that explains everything observed and predicts what will be observed next. But the subject has graduated decisively out of the realm of speculation into the realm of empirical inquiry. Scientists stopped calling extraterrestrial intelligence a theory because the language of theory implies a framework that is being tested. What now exists is something different, a set of observations that demand explanation, and a growing recognition that some of those explanations may not fit comfortably within the assumptions that astronomy has historically made about what kinds of phenomena occur in the universe. For decades, the dominant framing of the search for extraterrestrial intelligence centered on what was called the Great Silence. The apparent fact that despite extensive efforts to detect signals from other civilizations, no clear, confirmed, repeatable signal had been found. The silence was treated as data. It was incorporated into the Fermi paradox, the puzzle of why, if intelligent life is common, we have not detected it. Various explanations were proposed for the silence. Perhaps civilizations are rare. Perhaps they destroy themselves before achieving the capacity for interstellar communication. Perhaps they exist but choose not to broadcast. Perhaps the timing is wrong, and we are searching at a moment when no detectable signals happen to be reaching Earth. The framing of cosmic silence shaped public perception of the search for extraterrestrial intelligence for generations. It implied that the universe had been listened to, carefully, and that nothing had been heard. It suggested that the absence of evidence was evidence of absence, or at least evidence of profound rarity. It made the search seem like a slowly failing project, one that had been conducted in earnest for decades and produced increasingly demoralizing results. This framing was always, in important ways, a lie. Not deliberate, not malicious, but structurally misleading in ways that obscured what the search had actually accomplished and what it had actually found. The lie began with the assumption that the search had been comprehensive. It had not. The total volume of the radio spectrum that has been searched, even with the most advanced instruments, represents a vanishingly small fraction of the possible frequencies durations, and sky positions where signals might exist. A famous calculation by the astronomer Jill Tarter compared the entirety of SETI searches over their first several decades to dipping a single 8-ounce glass into Earth's oceans and concluding that no fish exist because none happen to be in the glass. The comparison may understate the case. The volume of the search space, defined by all possible combinations of frequency, signal strength, transmission duration, sky direction, and signal encoding, is so vast that the searches conducted to date have sampled only an infinitesimal fraction of it. To claim that the universe is silent based on this sampling is to make a claim that the sampling cannot support. The lie continued in the treatment of signals that were found. Multiple anomalous signals have been detected over the decades of SETI operations. Some were eventually explained by natural phenomena or instrumental effects. Others were never explained. The 1977 WOW signal, a 72-second burst of narrowband radio emission detected by the Big Ear telescope in Ohio, has never been satisfactorily explained as a natural phenomenon and has never been redetected despite extensive efforts. The BLC-1 signal, detected by Breakthrough Listen in 2020 and apparently originating from the direction of Proxima Centauri, was eventually attributed to Earth-based interference, but the chain of reasoning that produced this attribution was not as straightforward as the public characterization suggested. Fast radio bursts, high-energy radio transients from distant galaxies, were considered exotic and inexplicable when first detected, and some of their properties continue to resist standard astrophysical explanations. The silence, in other words, was always punctuated. Signals were heard, some were dismissed too quickly, others remain unexplained. The framing of total silence served psychological and institutional purposes. It allowed the field to maintain a default skeptical posture and to avoid the consequences of taking individual anomalous signals too seriously, but it did not accurately describe what had been observed. The universe, as it turns out, has been speaking. The question is whether anyone has been listening carefully enough to understand what is being said. The scientific search for extraterrestrial intelligence began on a spring morning in 1960 at the National Radio Astronomy Observatory in Green Bank, West Virginia. The astronomer Frank Drake pointed an 85-foot radio telescope at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for signals at a frequency near 1,000 to 420 MHz. This frequency was not chosen at random. It is the natural emission frequency of neutral hydrogen, the most abundant element in the universe. And Drake reasoned that any civilization conducting astronomy at radio wavelengths would have discovered this frequency for the same scientific reasons that human astronomers had discovered it. If they wanted to communicate, this frequency would be a natural choice, a universal landmark in the radio spectrum that any technological civilization would notice. The project, which Drake named Project Ozma after the Queen of the fictional land of Oz, ran for 4 months. It detected no confirmed signal of extraterrestrial origin. It did detect one anomalous burst that turned out to be a US Air Force communication, an event that taught early SETI researchers a critical lesson about the difficulty of distinguishing between genuine signals from space and various forms of human-generated interference. Project Ozma demonstrated something more important than any specific result. It demonstrated that a search for extraterrestrial intelligence could be conducted as a serious scientific endeavor with real instruments, real protocols, and real data. The question moved, in those 4 months, from the realm of pure speculation into the realm of empirical inquiry. In the decades that followed, SETI grew slowly and irregularly. Funding came and went. Various projects were initiated, conducted for periods of months or years, and then concluded or suspended. The Soviet Union conducted its own searches throughout the Cold War, often with different assumptions and methodologies than the American programs. NASA funded a major SETI program in the early 1990s that was cancelled by Congress after 1 year of operation. Private funding eventually became the primary source of support for ongoing SETI work, with the SETI Institute in California becoming the institutional home for much of the world's serious search activity. The Allen Telescope Array, funded primarily by Microsoft co-founder Paul Allen, was constructed in Northern California specifically to conduct SETI observations on a continuous basis. It came online in stages beginning in the mid-2000s and has been the primary instrument for systematic SETI searches in the United States for the past 2 decades. In parallel, the Breakthrough Listen initiative, funded with $100 million by the Russian-Israeli billionaire Yuri Milner, and launched in 2015, has provided the largest single infusion of resources into SETI in the history of the field, supporting observations at major radio telescopes around the world, including the Parkes Observatory in Australia, the Green Bank Telescope in West Virginia, and the FAST Telescope in China. The growth of SETI from a 4-month experiment with one telescope in 1960 to a continuous internationally distributed research program with hundreds of millions of dollars in funding represents one of the most dramatic shifts in scientific status of any research subject in recent history. The transformation has occurred largely without dramatic public announcements, without confirmed detections that would have made headlines, and without the kind of validation that other scientific fields receive when their predictions are spectacularly confirmed. It has occurred because the people working in the field have, year by year, refined the methodology, expanded the search space, improved the instruments, and quietly built an infrastructure capable of detecting signals that would have been undetectable a generation ago. The instruments are listening now in ways that earlier generations of SETI researchers could only have imagined. On the night of August 15, 1977 at 11:16 p.m. Eastern Time, the Big Ear radio telescope at Ohio State University detected a signal that has never been satisfactorily explained. The telescope was operated by the volunteer astronomer Jerry Amon, who was reviewing computer printouts of the night's observations several days after the event. The data from Big Ear consisted of long strings of characters representing signal strength at different frequencies and times. Most of the characters were zeros or low numbers indicating typical background noise, with occasional higher values for naturally occurring radio sources in the sky. What Amon noticed in the data from August 15th was a sequence of characters unlike anything else in the night's observations. The numbers indicated a signal far above background noise, roughly 30 times louder than the typical radio sky in that direction. The signal lasted for the entire 72 seconds that the relevant region of sky was in the telescope's beam, and its intensity profile matched exactly the pattern that would be expected from a real signal, originating in space, rising and falling as the rotation of Earth carried the target through the telescope's field of view. Amon circled the sequence on the printout and wrote the word "wow" in the margin, giving the signal the name by which it has been known ever since. The WOW signal had several characteristics that made it remarkable. It was narrow-band, concentrated in a very narrow frequency range, exactly the kind of profile that artificial signals tend to have and natural astrophysical sources tend not to have. It appeared in only one of the telescope's 2 receiver feeds, suggesting it came from a specific direction in the sky, rather than a diffuse source. It was at a frequency near the hydrogen line, close to 1420 MHz, the same frequency Frank Drake had chosen as a likely interstellar communication frequency in Project Ozma 17 years earlier. Its intensity profile matched the expected signature of a point source being scanned by Earth's rotation. Every property of the signal was consistent with a transmission from space and inconsistent with the natural radio sources that radio astronomy was familiar with. Despite extensive efforts in the years since 1977, the WOW signal has never been detected again. The Big Ear telescope itself was decommissioned in 1998, and follow-up searches conducted by other telescopes, including the Very Large Array in New Mexico, the Mount Pleasant Radio Observatory in Tasmania, and various antennas operated by Breakthrough Listen have all returned negative results. Whatever produced the signal occurred once in 1977 and has not occurred again in a way that any subsequent observation has detected. The WOW signal sits in an uncomfortable middle ground between confirmed detection and dismissible anomaly. It cannot be confirmed as an artificial signal of extraterrestrial origin because it has not been redetected, and because with only one observation, the alternative explanations cannot be definitively ruled out. It cannot be confidently dismissed because no natural source has been identified that would produce a signal with all the characteristics observed, and because the signal does not match the known signatures of human-generated interference at the time and location. For nearly 5 decades, it has remained the strongest single piece of evidence ever recorded for what might be an artificial signal from beyond Earth, while simultaneously refusing to provide the kind of confirmatory data that would resolve the question. It is a measurement that demands explanation and that no explanation has yet adequately provided. In the decades following the WOW signal's detection, multiple explanations have been proposed for what produced it, Each explanation has been examined, tested against the available data, and either ruled out or rendered inadequate by the specific characteristics of the signal. The accumulated record of these proposals tells a story not of a mystery being gradually solved, but of a mystery that has resisted every solution that has been seriously attempted. The most frequently proposed natural explanation involves comets. In 2017, the astronomer Antonio Paris published a paper arguing that a pair of comets, 266P/Christensen and 335P/Gibbs, were in the right region of sky at the right time and could have produced the observed signal through their hydrogen cloud emissions. The proposal received significant media attention. It also has serious problems. The hydrogen clouds surrounding comets do not produce narrowband emission at the relevant frequencies. They produce broadband thermal emission spread across a much wider frequency range. The intensity of cometary hydrogen emission is also far too low to account for the strength of the WOW signal. Multiple subsequent analyses by other researchers concluded that the cometary explanation is inconsistent with both the spectral and intensity characteristics of what was actually detected. The proposal has not been formally retracted, but it is not considered viable by most researchers who have examined the original data. Other natural explanations have proposed various exotic astrophysical phenomena: pulsar emissions from specific orientations, microlensing events that could have temporarily amplified a distant source, transient emissions from specific types of stellar activity. Each of these proposals fails on similar grounds. The signal characteristics are simply not consistent with natural sources, and the specific combination of narrowband emission, point source intensity profile, and proximity to the hydrogen line is exactly the combination that natural sources do not produce. The most plausible non-extraterrestrial explanations involve human-generated interference of some kind. Military radar, satellite transmissions, ground-based broadcasts reflected off space debris. These are the kinds of sources that produce narrowband signals at the intensities observed. The problem with these explanations is that the Big Ear team conducted careful surveys to identify and exclude known sources of interference, and no source matching the observed signal characteristics was identified at the time. The signal also did not appear in subsequent observations of the same region of sky despite extensive monitoring, which is inconsistent with most types of regular interference. Something would have had to produce the signal once in a specific direction, with specific characteristics, and never again, a pattern that is unusual for any human-generated source. What the WOW signal was not, with high confidence, was a routine astrophysical phenomenon. The properties of the signal exclude virtually all known natural sources of narrowband radio emission. What it was not, with somewhat less but still substantial confidence, was an obvious human interference source. The careful protocols of the Big Ear program, combined with the failure of subsequent surveys to identify any candidate interference source, leave the most common categories of explanation seriously weakened. What it might have been is a question that no available evidence can answer with certainty. The signal could have been an extraterrestrial artificial transmission. It could have been an unusual or unprecedented natural phenomenon that has not occurred again in observation. It could have been a form of interference that was never identified, despite the best efforts of the original observers. The absence of redetection means that the question cannot be resolved by analysing more data. There is no more data. The WOW signal remains, 4 decades later, as one of the most consequential ambiguous observations in the history of astronomy. It is the single observation that more than any other kept the question of extraterrestrial intelligence alive as a serious scientific subject during decades when the prevailing institutional attitude tried to push it to the margins. Every signal that is detected, every observation that is examined, every search that is conducted, takes place against the background of a question that physicist Enrico Fermi reportedly asked over lunch with colleagues at Los Alamos National Laboratory in 1950. The question was simple: where is everybody? Fermi's question was not idle speculation. It was a serious puzzle that emerged from the basic mathematics of the galaxy's age and size. The Milky Way contains roughly 400 billion stars. Many of these stars are billions of years older than the Sun. Even if interstellar travel is extraordinarily slow, moving at speeds far below the speed of light, a civilization that began spreading from a single star system at a fraction of light speed could colonize the entire galaxy in approximately 100 million years. This is a long time in human terms, but a short time compared to the age of the galaxy. The Milky Way has existed for roughly 13 billion years. There has been time for a galactic civilization to arise, spread, and reach Earth more than 100 times over. And yet, when we look at our solar system, we see no evidence of prior visitation. No alien probes, no abandoned bases, no clear signs that any other intelligence has been here. The galaxy appears, on this basis, to be empty in a way that the underlying mathematics does not predict. This is the Fermi paradox. The mismatch between the high probability of advanced civilizations and the apparent absence of any sign of them. The paradox is not resolved by any single answer. It is sharpened by the accumulating evidence that potentially habitable worlds are common, that the chemistry of life can arise under a wide range of conditions, that the basic ingredients for biology are scattered throughout the galaxy. The more we learn about the conditions for life, the more puzzling the silence becomes. The galaxy should be full of civilizations. The galaxy does not appear to be full of civilizations. Something is wrong with one of the premises. Multiple resolutions to the paradox have been proposed. Each one represents a different assumption about which premise is incorrect. The rare earth hypothesis suggests that the development of complex intelligent life requires a much rarer combination of circumstances than the basic biology assumes. The great filter argument suggests that there is some critical step in the development of communicating civilizations that almost no biological lineage successfully crosses, and that this filter might lie ahead of humanity rather than behind it, implying that the civilizations that approach our level of development typically destroy themselves before achieving interstellar capability. The zoo hypothesis suggests that civilizations exist, but have collectively chosen to avoid detection by emerging cultures, observing us without intervention. The dark forest hypothesis, which will be examined in detail later in this video, suggests that civilizations actively hide because the universe is dangerous and detection by hostile neighbors is fatal. Each of these resolutions has implications for how we interpret the signals we do detect. If civilizations are rare, then anomalous signals that cannot be explained naturally become more significant. They may represent unusual events from sparse populations, rather than typical communications from common neighbors. If civilizations actively hide, then the absence of clear, obvious signals is expected, and we should be searching for subtle signs of presence rather than dramatic transmissions. If the great filter lies behind us, then any signals we do detect should be more plentiful as we expand our search capabilities. The paradox is not just an abstract puzzle. It shapes the practical search for extraterrestrial intelligence by determining what kinds of evidence we should expect to find and how we should interpret what we do find. The question Fermi asked over lunch in 1950 still has no agreed-upon answer. It has become, in 70 years since, the question that hovers behind every signal, every observation, every search. The reason the question matters is not that it is unanswerable, but that the eventual answer, when it comes, will determine something fundamental about the nature of intelligence in the universe. In November of 1961, Frank Drake, the same Frank Drake who had pointed the Big Ear's predecessor at Tau Ceti and Epsilon Eridani the previous year, convened a small meeting of scientists at the Green Bank Observatory to discuss the question of extraterrestrial intelligence. The attendees included the chemist Melvin Calvin, who would receive the Nobel Prize in Chemistry the following month, the astronomer Otto Struve, the physicist Philip Morrison, and the young Carl Sagan, among others. Drake needed an agenda for the meeting, and to organise the discussion, he wrote on a blackboard a sequence of factors that, if multiplied together, would estimate the number of communicating civilizations currently existing in the Milky Way galaxy. The equation that resulted has been known ever since as the Drake equation. The structure of the equation is straightforward. It begins with the rate at which suitable stars form in the galaxy, multiplies by the fraction of stars that have planets, multiplies by the average number of planets per star that lie in habitable zones, multiplies by the fraction of those habitable planets where life actually develops, multiplies by the fraction of life-bearing planets where intelligent life evolves, multiplies by the fraction of intelligent civilizations that develop technology capable of detectable transmissions, and multiplies by the average length of time that such civilizations remain detectable. When Drake wrote the equation in 1961, every factor after the first one, the rate of star formation, which was reasonably well known, was almost entirely a matter of guesswork. There was no observational data on extrasolar planets at all. There was no understanding of how often life arises from prebiotic chemistry. The evolution of intelligence was understood only through the single example of Earth. The behavior of technological civilizations was understood only through human history. Every variable was a placeholder for a number that nobody knew. What the Drake equation provided, despite this complete uncertainty in its inputs, was a structure for thinking about the problem. It demonstrated that the question of how many civilizations exist is not a single mystery, but a chain of subsidiary questions, each potentially answerable through different kinds of investigation. The fraction of stars with planets could be determined by improved astronomical surveys. The frequency of habitable zones could be calculated from stellar properties. The probability of life arising could be probed by astrobiology and laboratory chemistry. The evolution of intelligence could be approached through evolutionary biology and the study of cognition in non-human species. Each variable became its own research program. Over the past 6 decades, several of those variables have moved from pure speculation toward genuine constraint. The rate of star formation in the galaxy is now well understood through detailed astronomical surveys. The fraction of stars with planets has been transformed by exoplanet detection. The answer turned out to be that virtually all stars have planets, and most have multiple planets. The number of planets in habitable zones has been estimated from exoplanet statistics. The answer appears to be a large number, plausibly billions in the Milky Way alone. The fraction of habitable planets where life develops remains unknown, but the discovery of extremophiles on Earth and the identification of complex organic chemistry in interstellar space have made the development of life seem less improbable than it once did. The fraction of life-bearing planets where intelligent life develops, the fraction of intelligent civilizations that develop detectable technology, and the average lifetime of technological civilizations all remain almost entirely speculative. These are the variables that depend on what is sometimes called the social science of the cosmos, the behavior of civilizations themselves, which we have only one example of and which we cannot generalize from with any confidence. Different reasonable assumptions about these variables produce answers ranging from millions of communicating civilizations in the galaxy to a single one. The Drake equation, today as in 1961, can be made to predict almost any answer depending on the assumptions used. What it cannot do is settle the question. The answer, when it comes, will not come from the equation. It will come from a signal. For most of the history of SETI, the question has been framed as a listening problem. The instruments are designed to detect signals from elsewhere, and the methodology has focused on receiving rather than transmitting. There is good reason for this asymmetry. Listening is passive and cheap. Transmission is expensive and, as some have argued, potentially dangerous. The famous theoretical physicist Stephen Hawking, among others, expressed concern that broadcasting Earth's location to the galaxy might attract attention from civilizations whose intentions could not be predicted. The argument for restraint in active transmission has shaped the field's overall posture. We are searching for messages, not sending them. There have been exceptions. On November 16, 1974, the Arecibo radio telescope in Puerto Rico transmitted a 3-minute message toward the globular star cluster M13, approximately 25,000 light-years away. The message was designed by Frank Drake and Carl Sagan with input from other scientists, and it was structured as a series of binary digits arranged in a way that, when properly decoded, formed a graphical representation of certain key facts about humanity and Earth. The numbers from 1 to 10 in binary, the atomic numbers of the elements that form the basis of life on Earth, the chemical structure of DNA, a stylized representation of the human form, a diagram of the solar system, an image of the Arecibo telescope itself. The message was designed not as a serious attempt at communication. At 25,000 light-years distance, no reply could possibly arrive for 50,000 years even at the speed of light, but as a demonstration that intentional transmission was technically possible and a symbolic gesture toward the universe. The transmission was timed to coincide with the rededication of the Arecibo telescope after upgrades. It was, in significant respects, more of an event than a serious communication attempt. But the Arecibo message established something that has continued to matter in the decades since. It demonstrated that the human civilization possessed both the technology and the institutional will to broadcast intentional signals to the cosmos. The boundary between species that listen and species that speak had been crossed, even if only briefly and symbolically. Other intentional transmissions have followed in the decades since. The cosmic call messages broadcast from the Evapatoria planetary radar in Ukraine in 1999 and 2003, the message from Earth transmission sent in 2008 to the exoplanet Gliese 581c, the various symbolic broadcasts conducted for cultural or educational purposes, but the question of whether humanity should be deliberately advertising its existence to the galaxy has never been resolved. The debate over intentional transmission, called active SETI or METI, messaging extraterrestrial intelligence, has divided the scientific community. Some argue that any sufficiently advanced civilization capable of receiving our signals would already have detected us through our incidental electromagnetic leakage, the radio and television broadcasts that have been radiating outward from Earth for over a century, the radar signals that probe the atmosphere, the spectroscopic signatures of an industrial civilization that are visible to any sufficiently sensitive observer. From this perspective, the question of whether to transmit is moot. We have been transmitting unintentionally for generations, and concerns about active broadcasts are closing a door that was already open. Others argue that the incidental signals are far weaker and far less detectable than intentional broadcasts, and that the difference between accidental leakage and a focused intentional transmission is the difference between background noise and a deliberate beacon. Under this view, intentional broadcasts represent a categorically different kind of self-disclosure, one that warrants careful consideration before being undertaken. What the Arecibo message established, regardless of one's position in this debate, is that the technical and conceptual problem of crossing from listening to speaking has already been solved. The question is no longer whether we can broadcast. The question is whether we should. In late April and early May of 2019, the Parkes Observatory in Eastern Australia was conducting routine observations as part of the Breakthrough Listen survey. The telescope was pointed at Proxima Centauri, the nearest star to the Sun, only 4.24 light-years away. Proxima Centauri is a red dwarf star with at least 3 known planets, including Proxima Centauri b, a roughly Earth-mass planet orbiting within the star's habitable zone. The system is among the most carefully studied stellar neighbourhoods in the galaxy, and the proximity of Proxima Centauri makes any potential biosignatures or technosignatures associated with it of particular interest. During the 2019 observation, the telescope's data processing pipeline flagged an anomalous signal. The signal was narrowband, concentrated in a frequency range of just a few hertz, which is exactly the kind of signal that artificial transmitters produce and that natural astrophysical sources almost never produce. It exhibited a steady drift in frequency that was consistent with the Doppler shift expected from a transmitter on a planet orbiting another star. It persisted for approximately 5 hours of observation, and it appeared only when the telescope was pointed at Proxima Centauri, disappearing when the telescope moved off target. The signal was given the designation BLC-1, Breakthrough Listen, Candidate 1, and it remained under analysis for over a year before any public announcement was made. The careful extended analysis was conducted because the signal had characteristics that genuinely matched what an extraterrestrial transmission would look like, and the Breakthrough Listen team wanted to be confident in their interpretation before any announcement. The eventual conclusion, published in 2 peer-reviewed papers in October 2021, was that BLC-1 was almost certainly the product of Earth-based radio interference. The detailed analysis identified that the signal's frequency, while drifting in a way that resembled Doppler shift from a planetary transmitter, also corresponded to multiple harmonics of frequencies known to be produced by ordinary electronics. The signal appears to be associated with an oscillator somewhere in the broader region around the observatory, and its apparent association with the Proxima Centauri direction was a coincidence of timing and geometry rather than a genuine astrophysical origin. The BLC-1 episode produced different reactions across different communities. Within the technical SETI community, it was treated as a validation of the methodology. The search had detected an interesting signal, the signal had been thoroughly analysed, and the analysis had correctly identified its mundane origin. This is precisely how a properly functioning search should work. In the broader public discussion, the episode was sometimes treated as disappointment or even a debunking of SETI more generally. Neither framing captures what the episode actually represented. What BLC-1 demonstrated, regardless of its ultimate explanation, was that the technical infrastructure of modern SETI is capable of detecting signals that look exactly like what an extraterrestrial transmission would be expected to look like. The signal had narrowband characteristics, persistent presence, Doppler-like drift, and apparent localization to a specific star system. If the signal had originated from interstellar space rather than from Earth-based interference, every characteristic measured would have been consistent with an extraterrestrial origin. The instruments are sensitive enough to detect such signals. The analytical pipelines are capable of flagging them. The protocols for follow-up and confirmation are robust enough to determine origin. This is the situation that the search now exists in. The infrastructure is ready, the methodology is mature, the instruments are scanning continuously, and the algorithms are processing the data in real time. When a genuine extraterrestrial signal arrives, if one arrives, the question of whether we will recognize it is no longer in serious doubt. The question is only whether the signal will come. In 2007, the astronomer Duncan Lorimer and his student David Narkovic were reviewing archival data from the park's radio telescope when they noticed something that did not match any signal they had seen before. Buried in observations from August of 2001 was a brief, intense burst of radio emission lasting only 5 milliseconds. That appeared to have originated far outside the Milky Way galaxy. The burst was so short that it had been overlooked in the original observation. It had taken 6 years for anyone to recognize what was in the data. The signal had characteristics that immediately marked it as extraordinary. The radio waves arrived at the telescope dispersed across a range of arrival times, a property called dispersion, which is caused by radio waves of different frequencies travelling at slightly different speeds through the ionized gas between stars. The amount of dispersion in the signal indicated that the radio waves had travelled through an enormous quantity of intergalactic plasma, far more than would be present if the source were located within our galaxy. The implied distance was on the order of 1 billion light-years. The signal had come from outside the Milky Way. This was unprecedented. Radio bursts of any kind from outside the galaxy had not previously been observed, and a burst lasting only milliseconds but containing enormous energy was not predicted by any standard astrophysical model. To produce a signal of that brightness over a distance of 1 billion light-years, the source would need to have released an extraordinary amount of energy in a very short period of time, more energy than the Sun produces in days, compressed into milliseconds. For several years after Lorimer's discovery, the signal remained unique. No similar burst had been detected, and the lone observation could not establish whether the event represented a new class of astrophysical phenomenon, an instrumental artifact, or something else entirely. Some astronomers were skeptical of the discovery. Others considered it potentially revolutionary but were unable to confirm or refute it without additional data. Then in 2013, the same Parkes telescope detected another similar burst. Then several more. With multiple events accumulating, the signals could no longer be dismissed as instrumental artifacts or isolated anomalies. They represented a genuine astrophysical phenomenon that occurred regularly throughout the universe, perhaps thousands of times per day across the entire sky, that simply had never been recognized because the bursts were too brief and the data analysis techniques required to find them had not been developed. The Lorimer burst, originally a single mysterious observation, became the prototype for an entire new category of astronomical event. Fast radio bursts, millisecond flashes of intense radio emission originating from distant galaxies, are now recognized as one of the most significant unsolved mysteries in modern astrophysics. Hundreds of them have been catalogued. Various sources have been proposed to explain them, including exotic stellar phenomena, magnetoflares, and more speculative possibilities. Some of those proposals have received support from subsequent observations. None has fully explained all of the properties of all of the observed bursts. The story of how the Lorimer burst was found and what it eventually revealed illustrates something important about the search for unusual signals. The signal had been there, in the data, since 2001. It took 6 years for anyone to recognize it, because nobody was looking for the specific kind of pattern it produced. The instruments were capable of recording it. The data were archived and available. What was missing was the recognition that this particular pattern in the data represented something real and significant. How many other signals are sitting in archived data, recorded by telescopes around the world over the past decades, waiting for someone to recognize what they are? The question has no certain answer, but the Lorimer burst demonstrates that the question is not theoretical. Signals can hide in plain sight for years until the right analysis is applied. In the years since the Lorimer burst was identified as the first known example of a fast radio burst, the study of these phenomena has grown into one of the most active fields in observational astrophysics. New telescopes have been built or repurposed specifically to detect them. Algorithms have been developed to find them in real-time data streams. Dedicated surveys have been mounted to catalogue as many as possible and to characterize their properties. The basic phenomenon, as it has been characterized over the past 15 years, is extraordinary. Fast radio bursts are intense flashes of radio emission, typically lasting between a fraction of a millisecond and several milliseconds, that originate from galaxies at distances ranging from a few hundred million to several billion light-years. The energy released in a single burst is comparable to what the Sun produces in days to weeks, compressed into milliseconds. The bursts are remarkably bright. They can be detected across cosmological distances despite their extreme brevity, because their radioluminosity is so high during the moment of emission. What has made fast radio bursts particularly puzzling is the diversity of their properties. Some bursts appear to be one-time events, detected once and never seen again from the same source. Others repeat, recurring from the same location in the sky, sometimes within hours or days, sometimes after years of silence. The repeating bursts and the apparently non-repeating bursts may represent different populations of objects, or they may represent the same kind of source observed under different circumstances. The data do not yet allow this question to be resolved. The energy required to produce a fast radio burst is so large that the source must be extraordinarily compact and energetic. Standard astrophysical phenomena that produce comparable energies, supernova explosions, gamma-ray bursts, the merger of compact objects, typically last from seconds to minutes, not milliseconds. To compress that much energy release into such a short time requires either an exceptionally compact source or an unusual emission mechanism. Several candidate sources have been proposed and partially supported by observations. Magnetars, highly magnetized neutron stars whose magnetic fields are trillions of times stronger than Earth's, the collisions of neutron stars, particularly energetic stellar flares, and more exotic possibilities including emissions from rapidly rotating black holes, and even, in the most speculative proposals, artificial signals from advanced civilizations using the radio bursts for technological purposes such as light sail propulsion of starships. The connection between fast radio bursts and magnetars received significant support in April 2020 when a fast radio burst was detected originating from within our own galaxy, from a known magnetar called SGR 1935 plus 2154. This was the first time a fast radio burst had been associated with a specific known object. The burst from SGR 1935 plus 2154 was less energetic than typical extragalactic fast radio bursts, but it had similar characteristic properties, and it strongly suggested that at least some fast radio bursts are produced by magnetar flares. However, the magnetar explanation cannot account for all of the properties of all of the observed bursts. The energy released in some extragalactic bursts substantially exceeds what magnetars are believed capable of producing. The repeating bursts in particular have characteristics that are difficult to reconcile with magnetar models. The mystery is not solved by the magnetar connection. It is partially explained with significant questions still outstanding. What fast radio bursts demonstrate beyond their specific physical characteristics is that the universe contains categories of phenomena that astronomy was completely unaware of as recently as 20 years ago. The instruments and analytical techniques to detect them did not exist. The theoretical frameworks did not predict them. They have always been occurring, thousands of them every day scattered across the sky, and human astronomy has only now developed the capability to notice. What else might be occurring that current capabilities cannot yet detect? This question has no answer. The answer, in some form, will be the next category of signal that astronomy learns to see. The first fast radio burst that was observed to repeat from the same location in the sky was designated FRB 121102. It was first detected by the Arecibo Observatory in 2012, and follow-up observations in 2015 and 2016 identified additional bursts from the same precise location on the sky. By 2020, hundreds of individual bursts had been detected from FRB 121102, all originating from the same source, a dwarf galaxy approximately 3 billion light-years from Earth. The discovery of a repeating fast radio burst was transformative. Until that point, all known fast radio bursts had been single events, and most theoretical models had assumed they were one-time catastrophic phenomena. A source that produced repeated bursts could not be a one-time event. The model of the source had to change. Whatever was producing FRB 121102 was a long-lived object capable of repeatedly generating bursts of energy in the milliseconds long, extraordinarily intense regime characteristic of fast radio bursts. The number of plausible candidate objects narrowed considerably. The burst from FRB 121102 did not occur on any predictable schedule. They were not periodic in the way that pulsar signals are periodic. They came in clusters, many bursts in rapid succession over hours or days, separated by quiet periods lasting weeks or months. This pattern made the source difficult to monitor continuously and required extensive observing time at major radio telescopes. But the cluster pattern itself was informative. It implied a source whose emission was modulated by some longer timescale process, perhaps an orbital period, perhaps internal activity cycles, perhaps interactions with surrounding material, that produced periods of high activity alternating with periods of relative quiescence. The localization of FRB 121102 to a specific dwarf galaxy and the subsequent identification of associated persistent radio emission from that location provided additional clues about the environment surrounding the source. The persistent emission suggested that the source is embedded in a region of high-energy activity, possibly a magnetar surrounded by debris from a recent supernova explosion, possibly an active region around a supermassive black hole, possibly something else entirely. The exact nature of the source environment remains an active area of research. Since FRB 121102 was identified as a repeater, several other repeating sources have been detected. The number of known repeaters is now in the dozens, and they appear to constitute a distinct subpopulation of fast radio burst sources. The bursts from repeating sources tend to have somewhat different characteristic properties from apparently non-repeating bursts. They're often somewhat less energetic, their spectra are somewhat different, their durations are slightly different. Whether the repeaters and the apparently non-repeating sources are two genuinely different categories of object, or whether they are the same kind of source observed under different conditions, remains uncertain. The discovery of repeating fast radio bursts has had implications beyond their specific physics. For the first time, astronomers have radio sources that produce intense, brief, recurring transmissions from precisely defined locations in the sky. This is, in a structural sense, exactly what an intentional artificial signal would look like if it were being broadcast from a specific source at unpredictable intervals. The repeating fast radio bursts are not believed to be artificial. The energies involved, the consistency with natural astrophysical models, and the lack of any patterns suggestive of encoded information all support natural origins. But the fact that the universe contains naturally occurring repeating radio sources with precisely localizable origins changes the way the search for artificial signals must be conducted. The distinction between a natural repeating source and an artificial repeating signal is not as obvious as it might once have appeared. What the repeating fast radio bursts have taught the field is that the universe itself produces signals that look superficially like what intentional transmissions might look like, and the methodology for distinguishing between them must continue to evolve as the observed phenomena become more complex. Before any signal can be seriously evaluated as a potential artificial transmission, the natural alternatives must be exhaustively considered. This is not merely procedural caution. It is the foundation of how the search for extraterrestrial intelligence is conducted, and it reflects a recognition that the universe is full of phenomena that human astronomy was unaware of until recently, that natural sources can produce signals with surprisingly artificial-looking characteristics, and that the cost of a false positive, claiming an artificial signal where none exists, is significant both for the credibility of the field and for the cultural impact of such a claim. The natural sources that are most relevant to the evaluation of candidate signals fall into a few major categories. Pulsars, rapidly rotating neutron stars whose magnetic fields beam radio emission across the sky like a lighthouse, produce extraordinarily precise periodic signals. Some millisecond pulsars are accurate enough to serve as timekeepers comparable to atomic clocks. The discovery of the first pulsar in 1967 by Jocelyn Bell Burnell was initially treated with some suspicion because the regular pulses seemed too artificial to be natural. The source was briefly nicknamed LGM1 for Little Green Men. The eventual identification of pulsars as rapidly rotating neutron stars established that nature can produce extraordinarily regular periodic radio signals. Magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's, are the apparent source of many fast radio bursts and a range of other intense electromagnetic phenomena. Their flares can release more energy in seconds than the Sun produces in years, and the brief, intense nature of their emissions can resemble the kind of focused transmission that an artificial signal might produce. The 2020 detection of a fast radio burst from a known galactic magnetar established that magnetars produce signals previously thought to require more exotic sources. Black holes, both stellar mass and supermassive, produce a wide range of electromagnetic signatures, from steady jets of high-energy radiation to dramatic transient events when matter falls into active galactic nuclei, the centers of galaxies hosting actively feeding supermassive black holes, produce signals across the electromagnetic spectrum that can be highly variable and that match no simple natural model. The category of natural sources also includes various more exotic phenomena: tidal disruption events when stars are torn apart by black holes, the mergers of neutron stars and black holes detected through both gravitational waves and electromagnetic radiation, plasma instabilities in the interstellar medium, and stellar flares from highly active stars. Each of these can produce signals with characteristics that, at first glance, might be mistaken for artificial transmissions. This is the background against which candidate signals must be evaluated. Any narrowband signal, any repeating pulse, any signal with apparent Doppler-like drift, any cluster of bursts from a localized source, each must be checked against the catalogue of known natural phenomena to determine whether it could plausibly originate from a natural source. The methodology of SETI has evolved to make this evaluation rigorous and reproducible, and the credibility of any future detection of an extraterrestrial signal will depend entirely on the strength of the argument that the signal cannot be explained by any natural source. The accumulating catalogue of natural radio sources has made the evaluation of candidate signals more difficult, not easier, in some respects. Each new category of natural phenomenon adds another potential explanation for any unusual signal. The universe has turned out to be more dynamic and more varied in its electromagnetic outputs than earlier generations of astronomers imagined, and the boundary between what is clearly natural and what might be artificial has shifted accordingly. A signal that would have been considered strongly artificial looking in 1970 might now have multiple plausible natural explanations. This is not a problem for the search, and it is what scientific progress looks like, but it has made the standard for confident identification of artificial signals significantly higher than it was a generation ago. Despite the expansion of the catalogue of natural radio sources, certain signals that have been detected over the past several decades have resisted every natural explanation that has been seriously proposed. These are not necessarily the most famous signals. The WOW signal, BLC1, and the various publicly discussed candidates have all received extensive coverage. The more interesting category may be the signals that are technical anomalies in the data of major surveys that are quietly investigated for years without public discussion, and that ultimately remain unexplained without being formally identified as candidates for extraterrestrial origin. These signals share certain characteristics. They are typically narrowband, concentrated in frequency ranges of a few hertz or less, which is the characteristic signature of artificial transmissions, and not of natural astrophysical sources, which generally produce broadband emission distributed across larger frequency ranges. They have signal strengths consistent with point sources at astronomical distances. They sometimes exhibit drift patterns consistent with the Doppler shifts that would be expected from transmitters on rotating bodies or in orbital motion. They often appear in the data only during specific observations of specific celestial directions, disappearing when the telescope moves off target. What distinguishes these signals from confirmed artificial sources is that they have not been redetected with sufficient frequency to allow detailed characterization, they have not been verified by independent observations from other telescopes, and they have not provided enough information content to be unambiguously interpreted as intentional communications. They are, in essence, signals that look like what an artificial signal might look like, but that lack the additional data needed to confirm that interpretation. The Breakthrough Listen project has identified multiple such signals over the past several years. Many of these have been eventually attributed to radio frequency interference of various kinds, but a residual category of unresolved candidates remains. The project's data archives contain numerous flagged events that have not been definitively classified, and the methodology for working through this backlog continues to evolve. The Allen Telescope Array, the FAST Telescope in China, the Meerkat Array in South Africa, and other major radio facilities have all detected anomalous signals that have not been formally categorized as either confirmed natural sources or artificial transmissions. Some of these may eventually be explained as instrumental effects or natural phenomena that are not yet well understood. Others may eventually be redetected and characterized in sufficient detail to allow confident interpretation. What this category of signals demonstrates is that the situation is not one of universal silence punctuated by occasional false positives. It's one of ongoing detection of signals that have characteristics consistent with potential artificial origin, that lack sufficient additional data to confirm their interpretation, and that accumulate in the archives faster than they can be definitively analysed. The search is producing candidates. The candidates are not being confirmed as artificial, but they are also not being confirmed as natural, and the residual pool of unexplained signals grows year by year. The honest characterization of the current state of the field is that the universe is sending detectable signals at a rate that exceeds the field's capacity to fully analyze them. Whether any of these signals are artificial in origin cannot be determined from current data. What can be determined is that the assumption of cosmic silence, on which much of the public understanding of SETI has been based, does not accurately describe what the instruments are actually recording. The instruments are detecting things. The interpretation of what those things are. In July of 2015, Israeli technology investor Milner stood on a stage alongside Stephen Hawking and announced an unprecedented commitment to the search for extraterrestrial intelligence. Milner pledged $100 million over 10 years to fund what he called Breakthrough Listen, a comprehensive, sustained, scientifically rigorous search for technosignatures across the nearest million stars, the entire galactic plane, and 100 nearby galaxies. The commitment was, by an order of magnitude, larger than anything that had previously been allocated to SETI in the history of the field. It established Breakthrough Listen as the most ambitious search ever undertaken and ensured that the methodology and infrastructure of SETI could be substantially modernized. The funding has supported observations at 3 of the world's most capable radio telescopes. The Green Bank Telescope in West Virginia, the largest fully steerable radio telescope on Earth with a dish 100 meters in diameter, has provided dedicated time to Breakthrough Listen since the program's inception. The Parkes Observatory in Australia, which had been the site of the Lorimer Burst discovery and many other significant detections, has similarly committed substantial time. The FAST telescope in China, the 500-meter aperture spherical telescope, the largest filled aperture radio telescope in the world, joined the project after its completion in 2016. Optical observations at the Automated Planet Finder telescope at the Lick Observatory in California complement the radio survey by searching for nanosecond laser pulses that could indicate optical communication or propulsion systems. The scale of the project is what distinguishes it from prior SETI efforts. Earlier searches typically involved limited observing time at single facilities, scanning small target lists or surveying limited regions of sky. Breakthrough Listen scans millions of stars across years of observation, generating petabytes of data that must be processed, archived, and analyzed. The computational infrastructure required for this analysis represents a substantial investment in itself, and the open-source release of much of the project's data has allowed researchers around the world to participate in the analysis. The methodological sophistication of Breakthrough Listen has also pushed the field forward. The project uses real-time data processing pipelines to flag candidate signals as they are detected, allowing rapid follow-up of interesting events. It implements rigorous protocols for distinguishing genuine astrophysical signals from radio frequency interference. It maintains comprehensive databases of confirmed interference sources to enable cross-referencing of new detections against known artifacts. The methodology has become a model for how serious searches for extraterrestrial intelligence should be conducted, and several other organizations have adapted elements of the Breakthrough Listen approach for their own searches. What Breakthrough Listen has not produced is a confirmed detection. Despite the most extensive search ever conducted, no signal has been verified as definitively extraterrestrial in origin. This is not a failure of the project. It is the expected outcome of any search if extraterrestrial transmissions are either rare, intermittent, or located outside the specific search parameters used to date. The negative result of Breakthrough Listen, to the extent it can be characterized as a negative result given that the search continues, places constraints on the prevalence of certain kinds of artificial signals in the observed search space, but it does not rule out their existence. What Breakthrough Listen has produced, more importantly than any specific finding, is the demonstration that serious, sustained, well-funded searches for extraterrestrial intelligence are possible. The project has established the institutional and methodological infrastructure for the field to operate at a scale that would have been impossible a decade ago. Whatever signals are eventually detected, by Breakthrough Listen, by other ongoing searches, or by future efforts, will be analysed using the techniques and standards that Breakthrough Listen has helped to develop. The field has been transformed by the existence of this project, regardless of whether any specific detection is ever confirmed. The volume of data produced by the modern radio telescopes has grown to a scale that makes human analysis essentially impossible. A single major facility like the Green Bank Telescope or the FAST Telescope produces terabytes of data per day during active observations. Across multiple facilities and continuous operation, the data volume produced by the world's radio astronomy infrastructure is measured in petabytes per year. Direct human review of this data is unthinkable. The role of human analysts has shifted entirely to designing, training, and supervising the algorithms that actually process the data. The algorithms that search this data for potential signals have grown enormously sophisticated. They incorporate machine learning techniques trained on known examples of signals and noise, allowing them to flag patterns that human analysts might miss. They implement increasingly rigorous filters to eliminate known sources of interference. They cross-reference candidate signals against multiple databases of known astronomical objects and human-generated transmissions to assess the plausibility of various interpretations. They produce ranked lists of candidate events that human researchers can then investigate in detail. What this means in practice is that the search for extraterrestrial intelligence is now conducted, in its first stages, almost entirely by software. Human researchers see only the candidates that the algorithms have flagged as worth investigating. The signals that the algorithms have classified as obvious interference, as known natural sources, or as below the threshold of interest are never seen by human eyes. They are processed, categorized and archived without further attention. This presents a problem that has become increasingly recognized within the field. The algorithms are trained on the kinds of signals that human researchers have decided to look for. If an extraterrestrial signal happens to have characteristics that match the trained model of what an artificial signal should look like, it will be flagged for review. If the signal has characteristics that the algorithms have been trained to classify as something else, as natural variation, as interference, as instrumental artifact, it will be filtered out before any human ever sees it. The question of what kinds of signals the algorithms might be missing is genuinely difficult to address. Any signal that does not conform to current expectations about what artificial signals should look like is at risk of being classified as something other than a candidate for extraterrestrial origin. A signal that uses an unfamiliar modulation scheme, that operates at an unexpected frequency, that has a duration or repetition pattern outside the trained model, any of these characteristics could cause the signal to be filtered out automatically. Some researchers have explicitly addressed this problem by designing alternative analytical approaches that look for anomalies in the data, without making strong assumptions about what artificial signals should look like. These approaches identify any signal that does not match known categories, rather than only signals that match a predefined model of what to expect. The challenge of these approaches is that they generate enormous numbers of anomalies, most of which are uninteresting, and the methodology for triaging them effectively is still being developed. What the algorithms are finding is being recorded, archived, and made available for analysis. What the algorithms are filtering out and discarding is by definition not being preserved in a form that allows later review. The decisions being made about what counts as a candidate signal and what counts as background are being made by software trained on assumptions that may or may not match what an actual extraterrestrial transmission would look like. Whether this matters, whether genuine signals are being filtered out by current algorithms, is an open question that cannot be answered from within the current framework. The search is being conducted at unprecedented scale, but the search is also constrained by the assumptions encoded in the analytical pipelines that conduct it. If civilizations are common in the galaxy, and if some of them are substantially older than humanity, then by various standard arguments the galaxy should appear, in some respects, to be inhabited. The arguments for this expectation have been made many times over the past several decades. A civilization spreading from a single origin at a tiny fraction of light speed could, given the timescales available, colonize the entire galaxy in approximately 100 million years, a long time in human terms, but a short time on galactic timescales. Even without active colonization, the cumulative electromagnetic radiation produced by an industrial civilization should be detectable across substantial distances. A galaxy full of advanced civilizations should look electromagnetically very different from a galaxy that contains only one. What we observe is not what such a galaxy should look like. The galaxy appears, in the relevant senses, to be quiet. The expected signatures of widespread advanced civilizations are not detected. The expected evidence of large-scale astroengineering projects is not observed. The expected accumulation of intentional and incidental transmissions across the radio spectrum is not present at the levels predicted by simple models of how civilizations should propagate. This observation, the galactic quiet zone, is the contemporary version of Fermi's question. Why does the galaxy look the way it does, given the underlying probabilities? Multiple resolutions have been proposed, each implying something different about the nature of civilizations and the conditions for intelligent life. One possibility is that civilizations are rare. The rare Earth hypothesis argues that the development of complex multicellular life requires a specific combination of conditions that may not be common: a stable single star, a large moon to stabilize axial tilt, a giant outer planet to shield the inner solar system from impacts, the right kind of plate tectonics to recycle nutrients, the right amount of radiation to drive evolution without overwhelming it. Under this view, the galaxy is not science because civilizations hide. It is science because civilizations are far less common than simple probabilistic arguments suggest. A second possibility is that civilizations are common but short-lived. The Great Filter argument suggests that there is some critical transition that most civilizations fail to navigate successfully. This could lie in the past: life arising from prebiotic chemistry, the emergence of complex cells, the development of language, or in the future in the form of self-destruction through nuclear war, environmental collapse, artificial intelligence, or other catastrophes that might lie ahead for humanity. If the filter lies ahead of us, the silence becomes ominous. It suggests that almost no civilizations survive long enough to be detected, and that humanity is likely to share that fate. A third possibility is that civilizations exist but actively conceal themselves. The zoo hypothesis, which will be discussed in detail later in this video, suggests that more advanced civilizations have collectively decided to avoid contact with emerging cultures like ours. The dark forest hypothesis suggests that civilizations conceal themselves because the universe is dangerous and visibility attracts hostile attention. Under either of these hypotheses, the silence is not absence. It is deliberate concealment by entities whose reasoning we do not understand. A fourth possibility is that we are searching incorrectly. Civilizations may communicate using methods, frequencies, or signal types that our instruments are not designed to detect. They may have transcended electromagnetic communication entirely in favor of methods we have not yet imagined. They may exist in regions of the sky we have not yet examined, at intensities below current detection thresholds, in forms we have not yet recognized. Each of these resolutions has different implications for the search and for humanity's place in the cosmos. Without more data, none of them can be definitively confirmed or rejected. The galactic quiet zone is a fact about what we observe. Its explanation remains open. In 1960, the physicist Freeman Dyson published a brief paper in the journal Science titled "Search for Artificial Stellar Sources of Infrared Radiation." The paper proposed a specific category of evidence that astronomers might look for in the search for advanced civilizations, not radio signals, not intentional transmissions, but the thermal infrared emission that would be produced by structures so large they captured the entire energy output of a star. The reasoning was simple. A civilization that grew significantly beyond its planet of origin would eventually need access to energy on scales far beyond what any single planet could provide. The total energy output of a star like the Sun is approximately 1 billion times what humanity currently uses across the entire planet. A civilization that could capture and use even a fraction of this energy would have access to power on scales that would allow extraordinary engineering, colonization of multiple star systems, construction of habitats containing trillions of inhabitants, scientific projects on scales impossible at human energy levels. The natural way to capture such energy would be to construct a structure or swarm of structures around the star itself, intercepting its radiation before it dissipated into space. Such a structure has come to be called a Dyson sphere, although Dyson himself preferred the term Dyson swarm, a vast collection of independent structures orbiting the star and collectively capturing much of its output. The exact configuration could vary. The defining characteristic from an observational standpoint would be that the visible light from the star would be reduced or eliminated, and the captured energy would eventually be re-radiated as waste heat in the infrared spectrum. A star with a Dyson structure around it would look to a distant observer like an unusually bright infrared source with reduced visible light, a thermal signature that natural stars do not produce. Dyson's proposal was, in its time, somewhat theoretical and speculative. It assumed that civilizations would grow indefinitely in energy use, that they would prefer engineering on stellar scales over alternative strategies, that they would use technologies whose waste heat would be detectable from interstellar distances. These assumptions are not obviously correct, and not all scientists studying the search for extraterrestrial intelligence find the Dyson sphere concept compelling. But the proposal had the virtue of suggesting a specific kind of observation that could be made, a search strategy that was implementable with infrared telescopes. In the decades since Dyson's paper, multiple surveys have looked for the infrared signatures of possible Dyson structures. The Infrared Astronomical Satellite, IRAS, launched in 1983, produced the first all-ski survey at infrared wavelengths and was used to search for candidate Dyson sphere signatures. Subsequent infrared surveys by the Wide Field Infrared Survey Explorer, WISE, and other instruments have continued this work. Tens of thousands of candidate objects with anomalous infrared excess have been catalogued. The vast majority of these have been explained by natural phenomena, circumstellar dust, evolved stars that are naturally bright in infrared, young stars surrounded by protoplanetary disks. A residual category of objects remains for which no satisfactory natural explanation has been identified. These unresolved infrared anomalies are not declared to be Dyson spheres. The methodology of the field demands that natural explanations be exhaustively considered before any artificial interpretation is seriously proposed. But the residual category exists, and as observational data accumulates, the catalogue grows. The search for the engineered signatures of advanced civilizations is conducted not as a single dramatic search, but as the ongoing analysis of vast survey databases looking for objects that do not fit any known natural category. What this search has produced to date is a catalogue of natural infrared sources, a few unresolved anomalies, and a methodology for distinguishing between natural and potentially artificial origins. What it has not produced is a confirmed detection of any structure that is incompatible with natural explanation. The galaxy, at the current level of observational completeness, does not appear to contain obvious large-scale engineering. Whether this means such engineering does not exist, or whether it means that the engineering is more subtle or different from Dyson's proposal than current searches can detect, is a question that cannot be resolved from within the current framework. The instruments are searching, the catalogues are growing, the answer, if one exists, remains to be found. In September of 2015, a group of astronomers led by Tabitha Boyajian at Yale University published a paper describing the unusual light curve of a star designated KYC 8462852, a star approximately 1,470 light-years from Earth. The star had been observed by the Kepler Space Telescope as part of its survey for exoplanets, and its brightness pattern over the years of Kepler observation had a feature that no other star in the survey exhibited: large, irregular, deep dips in brightness that occurred at unpredictable intervals. The dips were extraordinary. In some cases, the star's brightness dropped by more than 20%, far more than would be caused by any planet, which would typically produce dips of 1% or less. The dips were also irregular in shape and duration, lasting from days to weeks, with no periodic pattern that would suggest a regularly orbiting planetary companion. The light curve did not resemble that of any other star in the Kepler database, and it did not match any standard model of how planets, dust disks, or other natural phenomena should affect stellar brightness. The star, colloquially known as Tabby's star after the lead author of the discovery paper, became one of the most studied stellar objects in the galaxy in the years following the announcement. Multiple natural explanations were proposed. A swarm of fragmented comets passing through the system could produce irregular dimming events, though the timing and depth of the observed dips remained difficult to reconcile with cometary models. A circumstellar dust cloud of unusual geometry could produce similar effects. The star might be undergoing some unusual phase in its own evolution that produced internal variability not yet understood. A more speculative possibility was raised by the astronomer Jason Wright and his colleagues shortly after the original Boyajian paper appeared. They noted that the light curve characteristics were, in some respects, what might be expected from a partial Dyson sphere. a large-scale engineering project still under construction around the star, blocking varying amounts of starlight as different components of the structure passed across the star's disk as seen from Earth. The proposal was carefully framed not as a claim that this was the actual explanation, but as an observation that the data did not exclude the possibility, and that this was the kind of observation that would be most consistent with a partial construction Dyson structure if such a thing existed anywhere in the galaxy. The Tabby's star situation prompted multiple follow-up observations and analyses. The SETI Institute conducted radio observations of the star, finding no signs of artificial transmission. Spectroscopic studies attempted to identify the composition of any material blocking the starlight. Long-term photometric monitoring tracked the star's continued behavior. The accumulated evidence has, over the years since 2015, gradually favored natural explanations involving dust clouds of some kind. The detailed wavelength dependence of the dimming events is consistent with light being absorbed by small particles, and the long-term dimming trend observed in the star, which goes beyond just the dramatic dips, is most easily explained by accumulating dust in the system. The case is not entirely closed, however. The exact source of the dust, the specific physical configuration that produces the observed light curve, and the long-term evolution of the system are not fully understood. The natural explanations require somewhat unusual circumstances to match the observations, and the search for satisfying alternative explanations continues. What the Tabby's star episode demonstrated was not the discovery of an alien megastructure, but something more subtle, and possibly more important: the existence of astronomical phenomena that genuinely do not fit standard categories. The light curve of KYC 8462852 is real. Its characteristics are unusual enough that they have required the consideration of explanations ranging from natural dust clouds to speculative engineering. The fact that the most likely current explanation is natural does not erase the fact that for several years this was a genuine candidate for an artificial signature, and that the methodology of the field allowed it to be evaluated seriously as such. The search is producing candidates. The candidates are being evaluated rigorously. Most are being explained by natural sources. Whether any will eventually not be remains to be seen. On October 19, 2017, the Pan-STARRS telescope at Haleakala Observatory in Hawaii detected an object moving through the inner solar system on a trajectory that immediately marked it as something unusual. The object, designated 1I/2017 U1 and given the Hawaiian name Oumuamua, meaning scout or messenger from afar, was travelling at a speed and along a path that could not be explained by any solar system origin. Its trajectory was clearly hyperbolic, indicating that it had entered the solar system from interstellar space and would return to interstellar space after passing through. Oumuamua was the first object of confirmed interstellar origin ever detected within our solar system. The object was small. Estimates of its size range from approximately 100 meters to several hundred meters along its longest dimension. It was elongated, with a length-to-width ratio that astronomers initially estimated to be approximately 10:1, far more elongated than any natural solar system object that had been previously observed. It tumbled as it moved, suggesting a rotation period of approximately 8 hours. It exhibited dramatic brightness variations as it rotated, consistent with an object whose shape was strongly non-spherical and whose surface reflected light unevenly. These characteristics alone would have made Oumuamua significant, the first known interstellar visitor, with an unprecedented shape and unusual rotation. But the more remarkable observations came in the months following its initial detection. As astronomers tracked Oumuamua's trajectory after its closest approach to the Sun, they noticed that the object was not following the path that gravity alone would predict. It was accelerating slightly, in a direction that could not be explained by the Sun's gravity, or by the gravitational influence of any planet in the solar system. Something was pushing Oumuamua outward, beyond what the standard equations of orbital mechanics predicted. For comets, this kind of non-gravitational acceleration is well understood. As comets approach the Sun, ice on their surfaces vaporizes and produces jets of gas that act as natural propulsion, slightly altering their trajectories. The acceleration observed in Oumuamua matched the magnitude of what cometary outgassing might produce. The problem was that Oumuamua showed no other signs of cometary activity. Comets that produce enough outgassing to alter their trajectories typically also produce visible comas, clouds of gas and dust surrounding the nucleus, and tails extending behind them. Oumuamua produced neither. Multiple intensive observations searched for any sign of escaping gas or dust, and none was found. The anomalous acceleration of Oumuamua, without any accompanying signs of cometary activity, created a problem that no standard astronomical explanation could fully resolve. The Harvard astronomer Avi Loeb, then chair of Harvard's astronomy department, proposed an alternative explanation in 2018, that Oumuamua might be an artificial object, specifically a light sail or some other form of artificial structure whose surface area was large enough relative to its mass that solar radiation pressure could account for the observed acceleration. The proposal was controversial. It was also taken seriously enough to receive extensive technical analysis and to be published in peer-reviewed journals. Most astronomers who have studied Oumuamua remain skeptical of the artificial interpretation. Various natural explanations have been proposed, including the suggestion that Oumuamua might be a fragment of a hydrogen ice body that produced acceleration through outgassing of molecular hydrogen, which would be effectively invisible to observation. Each natural explanation has its own problems and requires somewhat unusual circumstances. The artificial explanation requires accepting that an interstellar object detected through human astronomy was the product of an extraterrestrial civilization. The natural explanations require accepting that the first interstellar object ever observed happened to have characteristics that strain conventional models. What Oumuamua demonstrated, regardless of its ultimate origin, is that the solar system is regularly visited by objects of interstellar origin. The discovery of Oumuamua was followed by the detection of TUI/Borisov in 2019, another interstellar visitor, this one a more conventional comet. These objects pass through the solar system constantly. We have only recently developed the capability to detect them. What other objects have passed through, undetected, throughout human history? Some of those objects, statistically, were likely larger and more interesting than the ones we have detected. The first object we caught had characteristics that nobody knew how to explain. What might the second, or the 10th, or the 100th look like? 2 years after Oumuamua passed through the inner solar system, the amateur astronomer Gennady Borisov detected another interstellar object using a homemade telescope at his observatory in Crimea. The object, designated TUI/Borisov, was the second known interstellar visitor to the solar system, and its discovery confirmed that Oumuamua had not been a unique event. Interstellar visitors were occurring regularly. The infrastructure to detect them was finally in place. TUI/Borisov was in many ways the opposite of Oumuamua. Where Oumuamua had been small, elongated, and showed no cometary activity, TUI/Borisov was substantially larger. Estimates of its nucleus ranged from approximately a few hundred meters to a kilometer across, and it was definitively a comet. It had a visible coma. It had a tail. As it approached the sun, it produced jets of dust and gas that were observed in detail by multiple telescopes, including the Hubble Space Telescope. Its composition could be analysed through spectroscopy of the material it released, and the chemistry of TUI/Borisov turned out to be remarkably similar to that of comets that originated in our own solar system. Carbon monoxide, water, cyanogen, the same molecules that characterise comets from the Oort cloud, were present in TUI/Borisov. This similarity was scientifically significant. It indicated that the chemical processes that produce comets in star-forming regions are universal, that the same basic chemistry occurs around stars throughout the galaxy. The compounds that make up comets in our solar system are also the compounds that make up comets in distant star systems. The implication for astrobiology is meaningful. The organic chemistry that may have contributed to the origin of life on Earth is the same chemistry that exists around other stars. The raw materials for biology are distributed throughout the galaxy, not concentrated in any particular region. TUI/Borisov also demonstrated that the detection of interstellar objects was no longer a fluke that depended on extraordinary luck. The improved survey telescopes that are now operating, including the Vera C. Rubin Observatory in Chile, which began full operations in 2025, are expected to detect many interstellar objects per year. The expected detection rate, based on the statistics of how often objects pass through detectable regions of the solar system, suggests that there may be hundreds or thousands of interstellar objects in the solar system at any given time, with new ones arriving and departing continuously. The vast majority are too small to be detected with current technology, but the detection threshold is improving rapidly. Each interstellar object that is detected is, in principle, a sample of material from another star system. The chemistry, structure, and history of these objects can in principle be analysed, and what is learned from them constrains the conditions in the regions of the galaxy where they originated. Some interstellar objects may have been ejected from their home systems billions of years ago, travelling between stars for periods longer than the existence of life on Earth. The materials in them are, in a sense, the oldest accessible samples of matter from outside our solar system, older than any rock or meteorite preserved by the cold of interstellar space for periods that dwarf any timescale humans normally consider. The detection of interstellar objects also raises the practical question of whether any of them could be intercepted by a spacecraft for direct study. A mission to rendezvous with an interstellar object would be challenging. The high velocities involved make orbit matching difficult, and the unpredictable trajectories make pre-positioning of intercept vehicles problematic. Several proposals have been developed for such missions, including the European Space Agency's Comet Interceptor mission, scheduled for launch in 2029, which is designed to wait at a Lagrange point until a suitable target is identified and then to be dispatched toward the object. The first direct study of an interstellar object, sampling it, photographing it from close range, analysing it in detail, may occur within the next decade. What such a study would reveal cannot be predicted in advance. The objects that pass through the solar system from interstellar space are a sample of the galaxy itself, in a form that human technology can potentially examine. They are not signals or transmissions, but they are physical contacts with material from beyond our own region of space. Whether any of them prove to be artifacts of civilizations rather than natural cosmic debris is a question that cannot be answered until such an examination is conducted. The opportunity for that examination is approaching. For most of the second half of the 20th century, the subject of unidentified objects in Earth's atmosphere was treated by mainstream science and government institutions with public dismissal, despite extensive private investigation. The US. Air Force's Project Blue Book, which operated from 1952 to 1969, investigated thousands of reports of unidentified flying objects, eventually concluding that most could be explained by misidentified natural phenomena, aircraft, or other mundane causes, though a residual category of cases remained unexplained. The official conclusion of Project Blue Book was that no UFO investigated had been a threat to national security, and that no evidence indicated extraterrestrial origin for any sighting. The program was terminated, and for several decades the subject was treated as essentially closed within official channels. This treatment of the subject was always somewhat at odds with the actual records of military encounters with unidentified objects. Pilots, radar operators, and other personnel continued to report encounters with objects exhibiting flight characteristics that no known aircraft could match. Extreme accelerations, lack of visible propulsion, instantaneous changes in direction, performance in atmospheric conditions that would destroy conventional aircraft. These reports accumulated quietly in classified files. They were not publicly discussed by the institutions that recorded them. They were not officially investigated as a serious phenomenon worthy of scientific attention. They simply existed in the records without resolution. This situation began to change in late 2017, when the New York Times published a report on a previously classified Pentagon program called the Advanced Aerospace Threat Identification Program, or AATIP. The program had operated from 2007 to 2012, investigating military encounters with unidentified objects and analysing the recorded characteristics of these encounters. The Times report included video footage of 3 separate incidents involving Navy pilots encountering objects that exhibited unusual flight characteristics. The footage had been recorded by aircraft sensors and had been classified for years. Its release into the public domain represented a significant departure from the long-standing official position that such encounters were either explainable or not worth serious investigation. The momentum of disclosure accelerated in the years that followed. In 2019, the Navy formally acknowledged the authenticity of the released footage and updated its protocols for reporting unidentified aerial phenomena, treating them as legitimate concerns rather than fringe reports to be discouraged. In 2020, the Department of Defense established the Unidentified Aerial Phenomena Task Force to coordinate the analysis of military reports. In 2021, the Office of the Director of National Intelligence delivered a preliminary report to Congress on UAPs, acknowledging that the phenomenon was real, that it represented a genuine challenge to US military operations, and that conventional explanations could not account for all observed cases. In 2022, NASA announced an independent study of UAPs conducted by a panel of scientists and engineers. By 2023, congressional hearings were being held in which military officials testified under oath about encounters with objects whose characteristics could not be explained by any known human technology. Former intelligence officers testified about decades-long programs to recover and study materials of unknown origin. The level of official acknowledgement of the subject had moved from sporadic and ambivalent in the early 2000s to systematic and ongoing by the mid-2020s. What this transformation represents is not a confirmation that extraterrestrial intelligence has visited Earth. The official reports and statements have consistently stopped short of any such claim. What they have established is that there are observed phenomena in Earth's atmosphere that current scientific and military understanding cannot fully explain, and that these phenomena are sufficiently real and sufficiently significant to warrant serious institutional attention. The question of what the phenomena actually are remains officially open. The question of whether they are real is, for the first time in decades, no longer in serious dispute within the institutions that have studied them. The series of official reports on unidentified aerial phenomena, released by the US government beginning in 2021, represent a category of document that did not previously exist. Formal acknowledgements by major military and intelligence agencies that unexplained phenomena are being observed and that the explanations remain elusive. These reports are not casual documents. They are produced under specific legislative mandates, reviewed through multiple layers of classification, and released to the public after the removal of information considered sensitive to national security. The first of these reports, the preliminary assessment delivered to Congress in June 2021, covered 144 reports of unidentified aerial phenomena observed by the military personnel between 2004 and 2021. The report categorized the observations and assessed what was known about each. Of the 144 cases analyzed, only one was identified as a clear case of misidentified balloon. The remaining 143 cases were classified as having insufficient data for confident identification, or as exhibiting characteristics that did not match known aircraft, atmospheric phenomena, or other explainable sources. The preliminary assessment described 5 potential explanatory categories for the unexplained cases: airborne clutter, birds, balloons, debris, natural atmospheric phenomena, US, government or industry developmental programs, foreign adversary systems, and a residual category labelled Other. The Other category included cases for which none of the first 4 categories provided plausible explanations. The report was careful to avoid speculation about what the Other category might include. The cases in that category, however, included some of the most striking encounters in the dataset. Incidents involving sustained observations of objects exhibiting flight characteristics that no known technology, foreign or domestic, has been demonstrated to possess. Subsequent reports expanded on this initial analysis. The Department of Defense annual report on UAPs, first delivered in October 2022, increased the total number of incidents under analysis to several hundred and provided additional detail on the characteristics observed. Some incidents involved objects observed simultaneously on visual sighting, radar detection, infrared sensors, and pilot eyewitness reports, multiple independent observation modes confirming the same phenomenon. Other incidents involved objects exhibiting apparent accelerations and maneuvers that would require G-forces destructive to any biological occupant and propulsion systems beyond current human capabilities. The reports have been notably careful in their language. They do not claim that any UAP is of extraterrestrial origin. They do not endorse any specific explanation. They consistently emphasize that the data on each incident is limited, that biases and observational errors may affect the records, and that confident identification requires additional information that is often unavailable. The reports are written in the careful hedged language of institutional documents that are designed to convey information without taking definitive positions on contentious interpretations. What has been withheld is at least as significant as what has been released. Multiple reports have referenced classified annexes and supplementary materials available only to cleared personnel. Whistleblower testimony has alleged that the publicly released reports represent only a small fraction of the actual records, that more sensitive material is classified at very high levels, and that some programs to study UAP-related materials exist outside the normal oversight structures. The 2023 congressional testimony of former intelligence officer David Grush alleged the existence of long-standing programs to recover and analyze materials of unknown origin, and asserted that biological remains had been recovered from some incidents. Grush's specific claims have not been independently verified, but his testimony was made under oath and was followed by formal whistleblower complaints submitted through legally protected channels. The full extent of what the US government and other governments know about UAPs is not publicly determinable from the released documents. What is determinable is that the official acknowledgement of the phenomenon as real, unexplained, and worthy of serious investigation has fundamentally changed the position of the subject within mainstream institutional discourse. Whether the explanations that ultimately emerge will involve advanced foreign technology, natural phenomena not yet understood, or origins beyond Earth, the question is no longer whether the phenomenon exists. The question is what it is. In the broader public discussion of evidence for extraterrestrial intelligence, the various categories of evidence often blur together in ways that obscure significant distinctions. Unidentified aerial phenomena observed by military pilots, radio signals analysed by SETI researchers, anomalous interstellar objects detected by telescopes, atmospheric biosignatures identified on distant planets. These are different categories of evidence, observed through different instruments, evaluated by different methodologies, and supporting different kinds of conclusions. The accumulating case for extraterrestrial intelligence is built across these categories, but each requires evaluation on its own terms. UAPs, the contemporary term used to replace the older UFO designation, refer specifically to objects or phenomena observed in Earth's atmosphere or near-Earth space that cannot be identified through conventional analysis. The category is defined by what we do not know rather than what we do know. A UAP is, by definition, unidentified. It might eventually be identified as a conventional aircraft seen under unusual conditions, an atmospheric phenomenon not yet well understood, a foreign military system, or something more exotic. The category encompasses all genuine cases of failed identification, without committing to any particular explanation. UFO, unidentified flying object, is the older term that carries cultural baggage from decades of conspiracy theories, popular culture portrayals, and contested claims. The terminological shift to UAP was made in part to distance current official analysis from the cultural associations of UFO discussions, and to encourage serious investigation without the connotations attached to the older term. Alien signals, the focus of much of this video, refer specifically to electromagnetic transmissions or other signals from cosmic distances that might indicate the existence of intelligent civilizations beyond Earth. The category is defined by location. These signals originate from beyond Earth's atmosphere, typically from interstellar or intergalactic distances, and by nature, they are signals in the technical sense, electromagnetic emissions, or other physical signals that can be detected and analysed by scientific instruments. The evidence for these categories comes from very different sources and has different epistemological status. UAP evidence comes primarily from military and civilian aviation reports, supported by radar records, sensor data, and pilot observations. The evaluation of this evidence involves considerations specific to atmospheric flight, military observations, and the reliability of human and instrumental witnesses to events occurring at close range. Alien signal evidence comes from radio and optical telescopes operating at frequencies and sensitivities far beyond ordinary human perception. The evaluation of this evidence involves astrophysical analysis, signal processing, and rigorous comparison with known natural sources of similar signals. Each category of evidence may, in principle, support conclusions about extraterrestrial intelligence, but the connection between the categories is not automatic. The existence of unexplained phenomena in Earth's atmosphere does not, in itself, demonstrate that they are of extraterrestrial origin. They might have explanations involving conventional technology, natural phenomena, or other terrestrial origins. The detection of an unexplained radio signal from a distant star system does not, in itself, demonstrate that the signal is artificial. It might have explanations involving exotic natural sources that are not yet well understood. The detection of biosignatures in a planetary atmosphere does not, in itself, demonstrate the existence of intelligent life. It might indicate microbial activity or non-biological chemistry. Each category of evidence carries its own interpretive challenges, and the connection between them requires its own analysis. What the convergence of these categories represents, however, is something significant. The accumulating evidence across multiple independent fields, atmospheric, electromagnetic, biological, geological, all points in the same general direction, that the universe contains phenomena that current understanding cannot fully explain, that some of these phenomena have characteristics consistent with the existence of intelligence elsewhere, and that the institutions and disciplines studying these phenomena are increasingly treating the question of extraterrestrial intelligence as a legitimate subject of inquiry. The various categories of evidence do not collectively prove the existence of alien civilizations. They collectively establish that the question deserves serious investigation, and that the institutional and methodological infrastructure to conduct that investigation has finally been built. In January of 2014, a meteor exploded over the Pacific Ocean near Papua New Guinea. The event was recorded by US government sensors monitoring atmospheric activity, and the data was eventually released as part of the broader trend toward declassification of UAP-relevant information. The meteor, designated CNEOS 2014-01-08 in NASA's Center for Near-Earth Object Studies database, had characteristics that distinguished it from the vast majority of meteor events recorded by global monitoring systems. Its velocity at atmospheric entry was extraordinarily high, approximately 60 km per second, well above the typical velocities of solar system meteoroids. The trajectory analysis indicated that this velocity was inconsistent with origins in the solar system, and the meteor was most likely interstellar in origin. This conclusion, that a small interstellar object had impacted Earth's atmosphere in 2014, was published in a peer-reviewed analysis by Harvard astronomer Avi Loeb and his student Amir Siraj in 2019. The analysis identified CNEOS 2014-01-08 as the first known interstellar meteor to have reached Earth, predating the discovery of Oumuamua by several years. The conclusion was disputed by some other astronomers, but in 2022 the US Space Command formally confirmed the interstellar origin of the meteor based on additional classified data not available to the original researchers. The interstellar origin became at that point an official assessment of a US government agency. Loeb recognized that a meteor of interstellar origin that had impacted Earth's atmosphere would have deposited material on the ocean floor at the impact location. If any of this material could be recovered and analyzed, it would constitute the first physical sample of an interstellar object ever obtained. The composition could be analyzed, the isotopic ratios could be measured, the structural and chemical properties could be characterized. Whatever the meteor had been, natural or artificial in origin, its remains could in principle reveal information about its source. Loeb organized and led an expedition in 2023 to search for material from the 2014 meteor along the Pacific Ocean floor. The expedition used a magnetic sled towed along the seafloor in the area of the calculated impact location. The methodology aimed to recover small spherical fragments, molten droplets that would have formed as the meteor disintegrated in the atmosphere, fallen into the ocean, solidified, and settled to the bottom. Such droplets, called meteorite spherules, are produced by most large meteor events and can sometimes be recovered if the impact location is known with sufficient precision. The expedition recovered hundreds of small spherules from the seafloor. Subsequent laboratory analysis of these spherules identified a subset whose composition differed from typical solar system materials. Some had unusual ratios of beryllium, lanthanum, and uranium, with high abundances of these heavy elements that are not commonly found together in meteorites from known solar system sources. Loeb and his collaborators interpreted these unusual compositions as consistent with an interstellar origin, possibly from a planet or asteroid with substantially different chemistry from solar system bodies. Some elements of Loeb's analysis remain contested. Other researchers have argued that the recovered spherules could have ordinary terrestrial or solar system origins, and that the unusual chemistry has alternative explanations. The interpretation of the recovered material is an active area of scientific debate, and the final assessment of what the spherules represent will require ongoing analysis and replication. What the expedition demonstrated, regardless of the eventual conclusion about specific spherules, is that the search for evidence of extraterrestrial origin can be conducted through means other than electromagnetic monitoring. Physical samples of interstellar matter can be recovered when impact locations are known with sufficient precision. The methodology for finding and analyzing such samples is being refined. The question of what to look for, what compositional signatures might distinguish an artificial origin from a natural one, what trace elements or isotopic ratios might indicate manufactured rather than naturally formed materials, is being seriously addressed for the first time. The search has expanded from the electromagnetic spectrum to physical samples, and the methodology continues to develop. In July of 2021, Avi Loeb announced the formation of the Galileo Project, a privately funded research initiative based at Harvard University and dedicated to the systematic scientific study of evidence for extraterrestrial technological civilizations. The project's stated mission was to bring the analysis of unidentified aerial phenomena and possible artifacts of extraterrestrial origin into the mainstream of scientific research, applying the standard methodologies of physics, astronomy, and engineering, rather than treating the subject as the domain of speculation or amateur investigation. The Galileo Project's approach is methodologically distinctive in several respects. Rather than relying on military or government data, much of which is classified and inaccessible, the project is building its own dedicated observation infrastructure, networks of optical, infrared, and audio sensors designed to detect and characterize unusual aerial phenomena in real time. The first such observatory was constructed at Harvard, with additional installations planned for various locations to provide comprehensive coverage of the atmospheric domain. The data from these instruments is open and available to researchers, providing a transparent alternative to the constrained official datasets that have driven much of the UAP discussion. The project also conducts theoretical research on possible signatures of extraterrestrial civilizations. What kinds of artifacts might be detectable? What observational characteristics might distinguish artificial objects from natural phenomena? What evidence might be expected from various scenarios of extraterrestrial visitation or contact? This theoretical work is essential because the field has historically lacked clear criteria for what kinds of evidence would or would not be compelling, and many disputes about specific cases have turned on disagreements about what should count as evidence at all. A third component of the Galileo project is the systematic analysis of interstellar objects passing through the solar system. The project has been involved in the studies of Oumuamua, the 2014 interstellar meteor, and other detected interstellar objects, applying both standard astrophysical analysis and the more speculative possibility of artificial origins. The systematic consideration of artificial explanations alongside natural ones as competing hypotheses to be evaluated against the evidence is itself a methodological innovation that the project has helped to legitimize. The Galileo Project's approach has received both support and criticism within the scientific community. Supporters argue that the subject of extraterrestrial intelligence has been excluded from serious scientific investigation for too long, that the accumulating evidence merits institutional attention, and that the application of standard scientific methodology to questions previously considered fringe is exactly what science should be doing. Critics argue that the project's interpretation of various observations is too aggressive, that natural explanations have been insufficiently considered in some cases, and that the framing of the research risks confirmation bias. Both views capture something real. The Galileo Project does represent a significant institutional commitment to taking the subject of extraterrestrial intelligence seriously as a scientific question. It also operates in a domain where the standards of evidence are difficult to specify in advance, and where reasonable researchers can disagree about how to interpret specific observations. What the project has clearly accomplished is the establishment of a research infrastructure dedicated to the question, the production of peer-reviewed analyses of specific cases, and the participation in mainstream scientific discourse on subjects that were previously excluded from such discussion. Whether the Galileo Project will produce a definitive detection of extraterrestrial intelligence remains uncertain. Whether it has already produced data, or, when fully analysed, will demonstrate such a detection is similarly uncertain. What the project has established is that the subject can be approached with serious scientific methodology, that the resulting analyses can be published in peer-reviewed venues, and that the question of extraterrestrial intelligence belongs within the legitimate scope of modern scientific research. This institutional shift may, in the long run, prove more consequential than any specific finding the project produces. The search for extraterrestrial life proceeds along two parallel tracks that pursue different categories of evidence. Biosignatures are observational signs that biological activity is occurring or has occurred on another world. Technosignatures are observational signs that a technological civilization has existed or currently exists. Both categories are legitimate targets for scientific investigation, but they require different methodologies, different instruments, and different criteria for confident detection. Biosignatures focus on the chemistry and conditions that suggest the presence of life. The most prominent target is the atmospheric composition of exoplanets, the chemical mixture of gases that surrounds another world. Certain combinations of gases are difficult to maintain without ongoing biological activity. Oxygen and methane, for example, react with each other rapidly in atmospheres, and the simultaneous presence of both in significant concentrations would indicate that something is replenishing them. Most plausibly, biological processes producing them faster than the chemistry can destroy them. Earth's atmosphere contains both oxygen and methane in unusual quantities precisely because life produces them. The James Webb Space Telescope and various ground-based observatories are now capable of analyzing the atmospheres of exoplanets in detail, particularly when those planets pass between their star and Earth in transit events. Spectroscopic analysis of the light filtering through the planetary atmosphere during transit reveals the absorption features of various molecules, allowing the chemical composition of the atmosphere to be determined. The search for biosignatures through this method is intensifying as observation time on appropriate telescopes is allocated to target planets. Technosignatures focus on signs of technological activity. The most familiar technosignature targets are radio and optical transmissions, intentional or incidental electromagnetic emissions from a technological civilization. SETI searches for technosignatures by scanning the electromagnetic spectrum for signals that have characteristics inconsistent with natural sources. Other technosignature targets include the thermal signatures of Dyson spheres, the atmospheric pollution that an industrial civilization might produce, the artificial light that might be visible on the night side of an inhabited planet, and structures of various kinds that might be detectable through specific signatures. The two approaches have different strengths and limitations. Biosignature searches can detect any form of life, including life that does not develop technology, microbial life, plant-like life, intelligent but non-technological life. They can detect life from the moment it emerges without requiring the long evolutionary trajectory toward technology. Their limitation is that they require the planet to be observable through transit or direct imaging methods, and they require the biological activity to produce detectable atmospheric or chemical signatures. Technosignature searches can detect civilizations across enormous distances, potentially across the entire galaxy, because intentional transmissions can be focused and amplified far beyond what natural processes produce. They can identify technological activity unambiguously when the signal characteristics are clearly artificial. Their limitation is that they only detect civilizations that produce detectable technosignatures during the period when our instruments are observing the right direction in the right frequency range, a vanishingly small fraction of all possible observation parameters. The two approaches are complementary. A biosignature detection without a technosignature would indicate life but not necessarily intelligence. A technosignature detection without a biosignature would indicate intelligence and technology, but might raise questions about the broader biological context of that intelligence. The combination of multiple detections across different categories of evidence would be substantially more compelling than any single detection in either category. The current state of both searches is one of expanded capability without confirmed detection. Biosignature analysis is producing intriguing but not definitive results for several exoplanets, including possible detection of dimethyl sulfide on K2-18b, a compound on Earth produced predominantly by the marine microorganisms. Technosignature searches are producing candidates that have not yet been confirmed, but the infrastructure for detection is more capable than ever before. The accumulation of negative results in both categories has not been definitive. It has not ruled out the existence of life or civilizations elsewhere. It has, however, established that obvious or abundant signs are not present at the levels that seemingly probabilistic arguments might suggest. What this means is open to interpretation. The search continues across both categories. The James Webb Space Telescope, launched in December 2021 and operating from the second Sun-Earth Lagrange point since 2022, has transformed the search for biosignatures in the atmospheres of exoplanets. The telescope's primary mirror, 6.5 meters in diameter, far larger than the Hubble Space Telescope's 2.4-meter mirror, combined with its sensitivity in the infrared spectrum and its location far from Earth's atmospheric interference, has made it the most capable instrument ever built for analysing the chemistry of distant planetary atmospheres. The method by which Webb analyses exoplanet atmospheres is called transmission spectroscopy. When an exoplanet passes between its host star and the telescope, a transit event, some of the starlight passes through the planet's atmosphere before reaching the telescope. Different molecules in the atmosphere absorb light at specific wavelengths, leaving characteristic fingerprints in the spectrum of the transmitted light. By measuring the spectrum during transit and comparing it to the spectrum when the planet is not transiting, the absorbing molecules in the atmosphere can be identified. The technique has been used since the early 2000s with various instruments, but Webb's capabilities have advanced the methodology far beyond what was previously possible. The telescope can detect molecules at concentrations and at distances that no previous instrument could probe. For nearby exoplanets in favourable orbital configurations, Webb can identify the major components of the atmosphere and constrain the abundances of various minor components. The list of detectable molecules includes water vapour, carbon dioxide, methane, carbon monoxide, ammonia, and several others, and importantly, certain combinations of these molecules that would suggest the presence of biological activity. Among the most studied targets for Webb's atmospheric analysis are the planets in the TRAPPIST-1 system. 7 Earth-sized planets orbiting an ultra-cool dwarf star approximately 40 light-years from Earth. Multiple TRAPPIST-1 planets lie within the habitable zone of their star, and their system represents one of the best opportunities to study Earth-like planets at relatively close range. Webb has conducted detailed observations of several TRAPPIST-1 planets, with results that have varied across the planetary system. Some TRAPPIST-1 planets appear to have no significant atmosphere, having been stripped of any gaseous envelope by stellar activity. Others have more substantial atmospheres whose chemistry is being characterized through ongoing observations. A particularly intriguing target has been K2-18b, an exoplanet approximately 124 light-years from Earth that orbits within the habitable zone of a red dwarf star. The planet is larger and more massive than Earth and falling into the category sometimes called sub-Neptune, but its conditions may include a global ocean covered by a hydrogen-rich atmosphere. Webb observations in 2023 detected carbon dioxide and methane in K2-18b's atmosphere, consistent with the conditions expected for an ocean-covered world. More controversially, the same observations produced a marginal but suggestive detection of dimethyl sulfide, a compound that on Earth is produced almost entirely by living marine organisms. The detection has not been confirmed at high confidence and has not been definitively interpreted as a biosignature, but it represents the kind of result that the Webb mission was specifically designed to produce. The cumulative impact of Webb's atmospheric analyses goes beyond any single observation. The telescope has demonstrated that detailed chemistry of distant planets is now a routine area of observation. The catalogue of analysed exoplanet atmospheres is growing rapidly, with each new dataset adding constraints on what kinds of worlds exist around other stars and what kinds of chemistries those worlds possess. The detection of a definitive biosignature has not yet occurred, but the methodology to detect such a signature is mature, and the survey of accessible targets continues. If life exists on a planet that Webb can study with sufficient detail, the chemistry produced by that life has a meaningful chance of being detected within the lifetime of the mission. The instruments are ready. The remaining question is what they will find. In September 2023, a team of astronomers led by Niku Madhusudan at the University of Cambridge published an analysis of James Webb Space Telescope observations of the exoplanet K2-18b. The paper, appearing in the astrophysical journal Letters, presented spectroscopic data showing the presence of carbon dioxide and methane in the planet's atmosphere. Substantial findings in themselves, indicating that K2-18b's atmospheric chemistry was consistent with the kind of world where complex chemistry could occur. The paper also reported what the authors described as a tentative detection of dimethyl sulfide, a finding that, if confirmed, would represent something far more significant. Dimethyl sulfide, abbreviated DMS, is an organic compound that on Earth is produced almost exclusively by living organisms, specifically by marine phytoplankton, microscopic algae that constitute the base of marine food webs. The compound is released into Earth's atmosphere by these organisms in enormous quantities, contributing to cloud formation and atmospheric chemistry. Non-biological processes can produce DMS in trace amounts, but the dominant source by orders of magnitude is biological. The detection of DMS in significant concentrations in an exoplanet's atmosphere would be, by Earth-based standards, one of the most compelling potential biosignatures that could be observed. The K2-18b detection was described as tentative for specific technical reasons. The spectroscopic signature of DMS overlapped with the signatures of other molecules that might be present in the atmosphere. The statistical significance of the detection was not at the level that would constitute a confirmed observation. Additional observations were required to either confirm or refute the initial finding. The authors of the original paper were careful to characterize their result as preliminary and as requiring further investigation, rather than as a confirmed biosignature. The reaction to the announcement reflected the complexity of how such findings should be communicated and interpreted. Some scientific outlets emphasized the possibility that the detection might represent evidence of life on another world. Other coverage emphasized the preliminary nature of the finding and the alternative explanations that would need to be ruled out before any biological interpretation could be confirmed. The Madhusudahan team's own statements were measured, presenting the result as consistent with possible biological origin, but not as proof of such origin. Follow-up observations of K2-18b have continued through 2024 and into 2025, with additional web observation time dedicated to refining the atmospheric analysis. The detection of DMS remains, as of the most recent publications, unconfirmed at high statistical significance. Some additional spectra have appeared to provide supporting evidence, others have not. The interpretation of the original detection has been complicated by the difficulty of distinguishing DMS from other compounds that produce overlapping spectroscopic signatures. What the K2-18b case demonstrates, regardless of how the specific question of DMS detection is ultimately resolved, is the structure of how biosignature science is now being conducted. Detailed atmospheric chemistry is being measured on planets light years away. The presence or absence of specific compounds, including compounds that on Earth are uniquely or predominantly produced by biology, is being assessed through real observations rather than theoretical speculation. These standards for confident detection are being established and applied. The methodology has graduated from what kinds of biosignatures might we someday detect, to what biosignatures are we detecting, and how do we evaluate the detections. If K2-18b's DMS detection is confirmed by subsequent observation, it will represent one of the most significant scientific findings in recent history. If it is not confirmed, if alternative explanations prove more consistent with the accumulating data, the methodology and instruments that detected the candidate signal will continue to operate and other candidates will emerge. The search has reached the level of capability where the question of biosignatures in exoplanet atmospheres is no longer abstract. It is being answered through observation, one planet and one spectrum at a time. 65 years after Frank Drake first wrote the equation that bears his name on a blackboard at Green Bank, the values of several of its key variables have been transformed by observation. The placeholder numbers that characterize the original formulation have been replaced in some cases by genuine measurements with quantified uncertainty. What this transformation means for the answer to the equation, for the estimated number of communicating civilizations in the galaxy, depends on how the remaining unknown variables are evaluated, but the constrained variables alone provide considerable information. The rate of star formation in the galaxy, R star in the original equation, is well constrained. Approximately 1 to 3 new stars are born per year in the Milky Way, with the rate having been somewhat higher in the past. Over the galaxy's lifetime, this rate has produced approximately 400 billion stars currently present in the galaxy, with many additional stars having been born and died over the past 13 billion years. The fraction of stars with planets, FP in the equation, was completely unknown in 1961. It is now understood to be very close to 1. Virtually all stars have at least some planets. The average number of planets per star appears to be at least 1 or 2, and many systems contain numerous planets of various sizes. The total number of planets in the Milky Way is likely in the trillions. The number of habitable planets per planetary system, NE in the equation, is also better constrained than it was in 1961, though significant uncertainty remains. The fraction of stars with at least one planet in the habitable zone, the range of orbital distances where liquid surface water could exist, appears to be substantial, perhaps 20 to 50% for the more abundant categories of stars. The Milky Way likely contains tens of billions of planets in habitable zones around their host stars. The fraction of habitable planets where life actually arises, FLL in the equation, remains essentially unknown. There are no confirmed detections of life outside Earth. Mars may have hosted microbial life in the distant past, but this is not confirmed. Various moons in the outer solar system have conditions that might support life, but no direct evidence has been found. Without any examples of life arising independently on different worlds, the actual rate of abiogenesis given habitable conditions cannot be empirically determined. The fraction of life-bearing planets where intelligent life develops, Fi in the equation, is constrained only by the example of Earth. Earth has hosted life for nearly 4 billion years, and intelligent life capable of communication and technology for perhaps 100,000 years, a tiny fraction of that period. Whether this represents a typical timeline, an unusually rapid emergence of intelligence, or an unusually slow emergence, cannot be determined from a single example. The fraction of intelligent species that develop detectable technology, Fc in the equation, is similarly constrained only by human history. Humanity developed radio technology in the early 20th century and has been capable of intentional transmission for approximately a century. Whether other intelligent species would follow similar trajectories or pursue entirely different technological pathways is not knowable. The average lifetime of communicating civilizations, L in the equation, is the variable that has perhaps the largest range of plausible values. Estimates have ranged from centuries, if civilizations are short-lived due to self-destruction or technological evolution beyond detectable transmission, to many millions of years. The value of L dominates the final answer to the equation when it is large and dominates the answer in a different way when it is small. Combining these variables with plausible assumptions for the unknown values produces estimates ranging from one civilization in the galaxy at any given time, making humanity essentially unique, to tens of thousands of simultaneous civilizations. The range reflects the genuine uncertainty in the unknown variables. What has changed since 1961 is that the lower range estimates have become more constrained by observation, and the upper range estimates have not been ruled out. This galaxy is not provably empty, and it is not provably crowded. The Drake equation today provides not a single answer but a range of possible answers, and the eventual resolution of the question requires data of a kind that the equation alone cannot provide. Throughout this video, the framing of cosmic silence has been examined and re-examined. The standard narrative, that we have listened to the universe and heard nothing, has been shown to be incomplete and partially misleading. The universe has produced signals that we have detected. Some of those signals have been explained, others have not. The accumulating catalogue of unexplained or anomalous observations does not constitute confirmed evidence of extraterrestrial intelligence, but it does demonstrate that the cosmos is not as quiet as the older framing suggested. A more careful examination reveals additional reasons to question the silence narrative. Several different categories of evidence are accumulating in ways that, taken together, suggest the situation may be substantially different from what the public framing has suggested. First, the data archives of major radio facilities contain large numbers of unexplained signals that have not been fully analysed. The volume of observations exceeds the capacity of researchers to investigate every candidate in detail. Many anomalous signals are flagged, characterized briefly, and then archived for possible later analysis. The processes for prioritizing which candidates receive extended scrutiny inevitably leave some unexamined. The signals that have been confidently identified as artificial, none to date, represent the small fraction that have been fully analysed. The much larger fraction that has not been fully analysed remains an unknown quantity. Second, the search has historically been constrained to specific frequency ranges, specific signal characteristics, and specific search strategies. Signals that fall outside these constraints would not be detected even if they were present. The space of possible artificial signals, across all frequencies, modulation schemes, duty cycles, signal strengths, and information encodings, is far larger than the space that has actually been searched. The negative result of finding no confirmed artificial signals applies only to the specific search space examined, not to the full space of possibilities. Third, the boundary between natural and artificial sources has become increasingly difficult to draw as the catalogue of natural phenomena has expanded. Phenomena that would have been considered strong candidates for artificial origin in earlier decades, fast radio bursts, certain pulsar signals, anomalous infrared sources, are now recognized as having natural explanations in many cases. But the natural explanations have themselves required postulating new categories of astrophysical phenomena that were not previously known. The natural and the artificial have not been clearly distinguished by accumulating data. Instead, the category of natural has expanded to absorb most of what was previously anomalous. Fourth, the consideration of artificial origins has been systematically discouraged in much of the scientific literature. Papers proposing artificial explanations for specific observations have often been treated as inappropriately speculative. Researchers who have publicly considered artificial interpretations have, in some cases, faced reputational consequences. The institutional pressures within astronomy have favoured natural explanations over artificial ones, often for legitimate methodological reasons, but with the cumulative effect of biasing the evaluation of candidate signals toward natural interpretations, even in cases where artificial explanations might be equally or more consistent with the available evidence. What this combination of factors suggests is that the cosmic silence we have heard is, at least partly, a silence we have chosen to hear. The instruments record more than we fully analyse. The search strategies cover less than the full space of possible signals. The natural explanations expand to absorb anomalies. The artificial interpretations are systematically discouraged. The cumulative effect is a framing of the data that emphasises the absence of confirmed detections over the abundance of unexplained observations. This is not a claim that the universe is, in fact, full of artificial signals that we are ignoring. The natural explanations for most observations are plausible and well supported. The discouragement of premature claims is methodologically appropriate. The silence may genuinely be sense, but it may also be something more complex, a partial silence, a constrained search, a careful interpretation that gives no credit to ambiguous candidates. The honest assessment is that we cannot yet determine which of these descriptions most accurately captures the situation. Among the proposed solutions to the Fermi paradox, the zoo hypothesis occupies an unusual position. It does not require modifying the underlying probabilities. Under the zoo hypothesis, advanced civilizations may be relatively common, but it explains the apparent silence by proposing that those civilizations have collectively chosen to avoid contact with humanity. The galaxy is not empty. It is, on this view, occupied by intelligences that have decided not to introduce themselves. The hypothesis is named for the analogy with terrestrial zoos and wildlife preserves, where human observers monitor and study animals while avoiding direct interaction. The proposed extraterrestrial behaviour would be similar. More advanced civilizations might observe emerging civilizations like ours, accumulate detailed knowledge of our development, and choose not to interfere with our trajectory. The reasons for such a choice could include ethical considerations about preserving natural development, practical concerns about the cultural impact of premature contact, scientific interest in observing how civilizations develop without intervention, or other motivations that humans might or might not anticipate. The zoo hypothesis has several features that distinguish it from other proposed solutions to the Fermi paradox. It does not require modifications to the underlying physics or astronomy. It does not require civilizations to be rare or short-lived. It does not require the failure of any specific transition in the development of intelligence. It simply postulates that the apparent silence is the result of deliberate policy by entities whose reasoning is sufficiently advanced or sufficiently different from ours that their choices appear, from our perspective, as silence. The hypothesis has been formally elaborated in various forms. The astronomer John Ball proposed the original version in 1973. Subsequent formulations have suggested specific mechanisms by which a galactic civilization might maintain a quiet zone around developing worlds, communication networks that bypass certain regions, observation protocols that minimize the chance of detection by emerging cultures, cultural traditions that establish non-interference as a norm across multiple civilizations spanning interstellar distances. What makes the zoo hypothesis difficult to evaluate is that it predicts exactly the observational situation we currently experience, a universe in which detailed search for intelligent life produces no clear positive results. Any evidence that might falsify the hypothesis, clear contact, unmistakable signals, observable interference with our development, would, under the hypothesis itself, be exactly what the more advanced civilizations have chosen to avoid producing. The hypothesis is, in some respects, unfalsifiable from our current vantage point, which is itself a source of legitimate skepticism about whether it constitutes a genuine scientific proposal. Variations of the zoo hypothesis address some of these difficulties. The interdictor hypothesis suggests that a specific civilization or group of civilizations actively enforces non-contact policies, not by collective agreement, but by maintaining a quarantine zone around developing worlds. The estivation hypothesis suggests that advanced civilizations enter periods of dormancy, waiting for cosmic conditions to become more favorable for advanced computation, and that we exist during such a dormancy period. The planetarium hypothesis suggests, more radically, that our entire observable cosmic environment might be a constructed illusion maintained by advanced civilizations for purposes unknown to us. Each variation accepts the basic zoo framework. Civilizations exist but are not visibly present, while proposing different specific mechanisms for the absence. The zoo hypothesis cannot be confirmed by available evidence. It also cannot be definitively ruled out. It exists as one of the possible explanations for the data we observe, neither demonstrably true nor demonstrably false. What it represents in the larger discussion is a reminder that the question of why we do not detect advanced civilizations does not necessarily reduce to questions about whether such civilizations exist. The answer might lie not in their absence, but in their deliberate decisions, in policies that have nothing to do with the technical capabilities of detection, and everything to do with choices made by entities whose reasoning may not be transparent to us. The Chinese science fiction author Liu Cixin, in his trilogy beginning with the three-body problem, proposed a solution to the Fermi paradox that has become known as the dark forest hypothesis. Although the framework was popularized through fiction, it has been seriously discussed by some researchers as a possible explanation for the apparent silence of the universe. The proposal is bleak, internally consistent, and unsettlingly difficult to refute on its own terms. The dark forest hypothesis rests on several assumptions about how civilizations would behave in a universe of finite resources and uncertain intentions. The assumptions are that survival is the primary motivation of any civilization, that the universe contains finite resources that cannot grow indefinitely, that civilizations cannot reliably determine the intentions of other civilizations they detect, and that any civilization, given sufficient time, can develop technology to destroy other civilizations across interstellar distances. If these assumptions hold, the hypothesis argues, the rational strategy for any civilization is to remain undetected. A civilization that broadcasts its existence reveals its location and approximate technological capabilities to all other civilizations in detection range. If even one of those other civilizations decides that the broadcasting civilization represents a potential threat, and the impossibility of reliably determining intentions means this calculation cannot be made with certainty, the rational response is preemptive elimination. The civilization that broadcasts has placed itself at the mercy of every potential receiver. The civilizations that survive are the ones that listen carefully and never speak. The metaphor of the dark forest captures the proposed dynamic. Each civilization is a hunter in a dark forest, armed and listening, aware that other hunters may be present, but unable to determine where they are, or what their intentions might be. Any hunter who reveals his position by speaking or making a fire becomes a target for any other hunter in the forest. The forest is silent not because there are no hunters in it, but because the hunters who survive are the ones who have learned not to make noise. Applied to interstellar distances, the dark forest hypothesis suggests that the apparent silence of the universe reflects not the absence of civilizations, but the deliberate concealment of civilizations that have learned the cost of being detected. The detectable transmissions, intentional broadcasts intended to communicate with others, are produced only by civilizations that have not yet learned the dynamics of the dark forest, and those civilizations are quickly eliminated by older civilizations that have. The survivors are silent. The galaxy appears quiet because the loud civilizations are dead. The hypothesis has significant implications for humanity's behavior. Earth has been broadcasting electromagnetic signals for over a century, radio, television, radar, and has conducted intentional transmissions including the Arecibo message and various subsequent broadcasts. Under the dark forest hypothesis, these signals have already announced our location to the galaxy, and if the hypothesis is correct, the consequences may already be unfolding on timescales appropriate to interstellar distances. The argument has been used by some commentators to suggest that any further deliberate broadcasting represents an existential risk to humanity. The dark forest hypothesis has serious problems as a complete explanation of the universe. The assumptions on which it rests are not universally accepted, and several aspects of the argument can be challenged. The assumption that survival is the primary motivation for all possible civilizations may not hold across the full diversity of intelligence that might exist. The assumption that civilizations cannot communicate their intentions reliably is challenged by the existence of mathematical communication and shared physical reality. The assumption that preemptive destruction is rational requires the specific game-theoretic conditions that may not always apply. Yet the hypothesis cannot be straightforwardly dismissed. The conditions it postulates, finite resources, uncertain intentions, the possibility of destructive technology, may apply across at least some plausible categories of civilization. The conclusion that silence is the rational strategy in the face of these conditions is logically valid under the stated assumptions. Whether the assumptions hold for the actual galaxy is an empirical question that cannot be answered without more data, and the data we have does not clearly contradict the hypothesis. The dark forest may not be the correct explanation, it may be incomplete or wrong about important details, but it may also capture something true about the calculus of survival in a universe of multiple civilizations, and the silence we observe may have meaning that older optimistic frameworks did not anticipate. The question of how humanity would respond to confirmed contact with another civilization has been considered seriously by scientists, sociologists, and policy researchers for decades. The considerations have varied based on the nature of the contact, a single confirmed signal versus ongoing communication, distant evidence versus direct visitation, friendly interaction versus indifferent observation, and based on different assumptions about how human institutions and cultures would actually respond to such an event. The honest assessment is that no one knows with confidence what would happen, but careful thought has produced several plausible scenarios that bear examination. The most extensively studied scenario involves the confirmed detection of an unambiguous artificial signal from interstellar space with no immediate possibility of direct contact due to the speed of light limitations on communication. This is the scenario most likely to occur, given the current state of detection capabilities and the typical interstellar distances involved. Under this scenario, the immediate consequences would be primarily cultural and intellectual rather than practical. Confirmation of the signal would represent the resolution of one of the deepest questions humans have asked. It would not, in itself, change the fundamental conditions of daily life or alter the practical capabilities of human civilization. The cultural and philosophical consequences, however, could be profound. Religious traditions would need to incorporate the existence of other intelligences into their theological frameworks, which would happen in different ways across different traditions. Some religious thinkers have already anticipated such as a discovery and developed compatible frameworks, others have not. The discovery would force a reckoning with the place of humanity in the cosmos that previous religious and secular worldviews have variously addressed or avoided. Scientific institutions would experience massive reorientation. The fields of astronomy, biology, and information science would have a new permanent direction of investigation. New disciplines would emerge to study the signal and its implications. Funding priorities across the sciences would shift to reflect the new significance of communication and contact research. The academic structures that currently study these subjects on a relatively modest scale would expand into something far larger. Political and economic responses would be more variable. Different national governments would respond differently, based on their own cultural contexts and political systems. International coordination, already established to some degree through SETI protocols developed by the International Academy of Astronautics, would face new pressures as the implications of confirmation became practical rather than theoretical. The protocols call for confirmation through multiple independent observations before public announcement, but the actual maintenance of secrecy during such confirmation has been questioned given the modern information environment. A more dramatic scenario involves contact with physical artifacts, or direct visitation, rather than electromagnetic signals at vast distances. The consequences of such contact would be substantially more disruptive than the signal detection scenario. The immediate practical effects could include the introduction of technologies, materials, or biological agents from outside Earth. The political consequences could include shifts in international power based on which nations had access to or control of the contact event. The cultural consequences could include rapid transformations of religious, philosophical, and economic systems based on the specific nature of what was contacted. The most extreme scenarios involve contact with hostile or indifferent civilizations whose intentions are not aligned with human survival. Such scenarios are speculative and rely on assumptions about extraterrestrial motivation that cannot be verified. They have been considered seriously, however, by some commentators who note that the asymmetry of capability between any civilization capable of interstellar contact and a civilization at humanity's current level of development would be such that an unaligned encounter could have catastrophic consequences for humanity, while presenting little risk to the more advanced civilization. What humanity would actually do in response to the confirmed contact depends on details that cannot be predicted in advance. The institutional, cultural, and political structures that would manage the response have been partially prepared but are not fully tested. The protocols developed by SETI researchers represent a serious attempt to anticipate the situation, but they cannot guarantee how actual institutions would behave when confronted with a real event. The most honest statement is that humanity is more prepared for this scenario than at any previous point in history, but that preparation remains incomplete. In the late 1980s, the International Academy of Astronautics began developing formal protocols for responding to a confirmed detection of an extraterrestrial signal. The resulting document, the Declaration of Principles Concerning Activities, following the detection of extraterrestrial intelligence, was adopted in 1989 and has been updated periodically since. It represents the most serious attempt by the international scientific community to anticipate and structure the response to confirmed contact, and its existence has been largely unknown to the general public despite its significance. The protocols address the situation in which a researcher or research team believes they have detected a signal of extraterrestrial origin. The first principle is that any such detection should be confirmed by the independent observation before any public announcement is made. The discoverer is expected to share data and observations with other researchers and institutions to allow verification by independent groups. This is the most basic and least controversial element of the protocols, the requirement of independent confirmation before claims of detection are made public. The protocols also address communication with international institutions. Confirmed detections are to be reported to the International Astronomical Union, the United Nations Secretary-General, and other relevant international bodies. This coordination is intended to prevent the disorder that might result from uncoordinated announcements and to ensure that the institutions with relevant authority are informed in a structured manner. The protocols do not require that detection be kept secret pending these notifications, only that the notifications be made promptly upon confirmation. The protocols address the question of response transmissions explicitly. They state that no response to any detected signal should be sent without the agreement of the international community, as expressed through appropriate institutional channels. This element of the protocols is more controversial than the confirmation requirements. Some researchers have argued that the right to respond should remain with the original detecting team or with the nation in which the detection occurred. Others have argued that response decisions affect all of humanity and must be made through international consultation. The protocols favour the international consultation view, but the protocols are not legally binding and could be circumvented in practice. The protocols are silent on certain critical questions. They do not specify how decisions about responses should actually be made, what voting procedures, what institutional structures, what timelines would govern the consultation. They do not specify what should be done if signals are detected by private actors or commercial entities rather than by institutional research programs. They do not specify what should be done in situations where the signal carries content that requires immediate response or that raises urgent ethical questions. They establish a framework but leave many implementation details unresolved. Their protocols have been tested informally on several occasions. The 1996 announcement of possible biosignatures in the Allen Hills 84001 meteorite from Mars, the 1997 WOW signal candidate event that turned out to be Earth-based interference, the 2020 BLC-1 candidate that was eventually attributed to interference. Each of these events involved decisions about timing of announcements, sharing of data, and engagement with media that approximated some elements of the formal protocols. None involved a confirmed detection of extraterrestrial origin, so the most consequential elements of the protocols have not been fully exercised. What the protocols represent is a recognition that the question of how humanity will respond to confirmed contact is not a question to be left to circumstance. The scientific community has thought seriously about the issue, has developed institutional frameworks, has established expectations for behaviour. The frameworks may prove inadequate when tested by actual events, but they exist as a starting point. They represent humanity's collective attempt, at least within the scientific community, to prepare for an event whose timing and nature cannot be predicted, but whose possibility has been taken seriously enough to merit institutional planning. The preparation is incomplete. It is also more substantial than most people realize. The transition from official denial to official disclosure regarding unidentified aerial phenomena has happened over a remarkably short time frame relative to the duration of the previous denial. For approximately 70 years following the end of the Second World War, the public position of the US government and most other governments on UAPs was that the phenomena either did not exist as anything beyond misidentification of conventional objects, or that they did not represent a national security concern worthy of serious study. The Air Force's Project Blue Book ended in 1969 with a public conclusion that no UFO investigated had been a threat or had been of extraterrestrial origin. For the following 4 decades, the official position remained essentially unchanged. Beginning in approximately 2017, this position began to change with unusual speed. The shift has not been a single event, but a series of disclosures, acknowledgements, and policy changes spanning multiple administrations and multiple agencies. Understanding why the changes occurred requires examination of several factors that have converged in roughly the same period. First, the documentary evidence in the form of recorded encounters had accumulated to a point where institutional secrecy had become difficult to maintain. The Navy and Air Force had been recording high-quality sensor data of UAP encounters for decades. The systems that recorded this data had evolved to produce evidence of types that were difficult to dismiss. Synchronized records from multiple sensors, observations confirmed by multiple personnel, video, and infrared imagery captured by modern aircraft. The volume and quality of this evidence had grown to the point where it was nearly inevitable that significant portions would eventually become public. Second, congressional pressure had grown for transparency about what the military was encountering. Congressional briefings on the subject had revealed enough to convince some members that the issue was significant, and these members began pushing for public reporting and oversight. The legislative environment shifted toward requiring formal reports and hearings on the subject, which produced the formal documents that have appeared since 2021. Third, the broader cultural environment had shifted to make the subject less stigmatized within mainstream institutions. The combination of declining religious authority, increasing public interest in science, and decades of cultural normalization of the question of extraterrestrial life had produced an environment where official acknowledgement of UAPs as a legitimate area of investigation was less politically dangerous than it had been in earlier decades. The career risks for officials who spoke seriously about the subject had decreased. Fourth, military and intelligence concerns had evolved. The increasing capability of foreign adversaries, particularly China and Russia, to develop advanced aerospace technologies had created a need to assess whether some observed UAPs might be foreign technological developments. This was a national security concern that required serious investigation, regardless of any extraterrestrial considerations. The official framing of UAPs as potential foreign capabilities provided a justification for systematic study that did not require commitment to any specific theory of origin. Fifth, internal whistleblowers within intelligence agencies had become more willing and capable of forcing transparency. The 2023 congressional testimony of former intelligence officer David Grush, alleging the existence of recovery programs and biological materials of unknown origin, was made through legally protected whistleblower channels and could not be easily dismissed. Other testimony from former officials with security clearances has accumulated, creating institutional pressure that earlier eras did not face. The cumulative effect of these factors has been a transformation in the official posture. The government has not formally acknowledged extraterrestrial origin of any phenomenon. It has, however, formally acknowledged that the phenomena are real, that conventional explanations do not account for all observed cases, and that systematic study is warranted. The transition from denial to disclosure has not produced confirmation of extraterrestrial visitation. It has produced a different intellectual environment, one in which the question can be seriously discussed within institutions that previously refused to engage with it. Throughout the period when the public framing of evidence for extraterrestrial intelligence was characterized by silence and absence, the evidence itself was accumulating in less visible ways. The pattern of this accumulation reveals something important about how scientific knowledge develops in contested areas. Knowledge often grows in the archives, in the unpublished analyses, in the work of researchers operating outside the spotlight of public attention. Only after the accumulation reaches a critical threshold does it become visible to the wider world. The accumulating evidence falls into several categories that, individually, would not be conclusive, but that, together, paint a different picture from the one of cosmic silence. The category of anomalous radio signals has grown considerably. The WOW signal of 1977 was treated as an isolated curiosity for decades. The discovery of fast radio bursts and their subsequent characterization as a genuine class of astrophysical phenomena demonstrated that the universe produces intense, brief signals from precisely localized sources. The catalogue of unexplained signals detected by Breakthrough Listen and other surveys, while not containing confirmed artificial signals, has grown to include numerous candidates that have not been definitively resolved. The number of signals that need to be explained has accumulated faster than the explanations have arrived. The category of biosignature candidates has also grown. The tentative detection of dimethyl sulfide in K2-18b's atmosphere is one example. Other observations of atmospheric chemistry on various exoplanets have produced candidates for non-equilibrium chemistries that would require ongoing production by some process, possibly biological, possibly not. The methodology for detecting and evaluating these signatures has matured. The targets for detailed study have been identified. The data are being collected with increasing sensitivity and detail. The category of interstellar objects passing through the solar system has emerged as a new line of evidence entirely. Oumuamua and 2I/Borisov represent the first confirmed members of a population that must contain many more objects. Each interstellar object is a sample of material from another star system, and the characteristics of these objects, their compositions, structures, behaviors, constrain what kinds of bodies exist around other stars. The next decade is expected to produce many more detections as new survey telescopes come online. The category of UAP reports has expanded dramatically with the release of military observation data. The accumulating record of encounters between military personnel and unexplained phenomena now includes hundreds of cases with multi-sensor confirmation. The phenomena exhibit characteristics that no known human technology has been demonstrated to possess. Whether these observations point to advanced foreign technology, natural phenomena not yet understood, or origins beyond Earth, the observations themselves are real, and they have not been adequately explained. The category of structural and engineering anomalies has grown more slowly but remains active. The infrared anomaly catalogues from various surveys contain unresolved cases. The light curves of various stars, including Tabby's star, have produced phenomena that strain conventional explanations. The search for evidence of large-scale astroengineering has not been definitively successful, but it has not been definitively negative either. The cumulative effect of these accumulating categories is significant. No single line of evidence, taken in isolation, would be sufficient to demonstrate the existence of extraterrestrial intelligence. Each category has natural explanations that, while sometimes strained, remain plausible. But the conjunction of multiple independent lines of evidence, all pointing in vaguely the same direction, represents a different epistemic situation from any one category alone. The honest characterization of the current state of evidence is that we have not confirmed the existence of extraterrestrial intelligence, but we have accumulated multiple categories of observations that demand explanation, and the explanations that have been offered have not, collectively, succeeded in resolving the question. The silence that we have been told characterize the search has been, in fact, a silence punctuated with signals whose interpretation is contested but whose existence is established. The next decade of observation and analysis is likely to be the most consequential period in the history of the search for extraterrestrial intelligence. The convergence of multiple developments, improved telescopes, expanded surveys, larger archives of data, sophisticated analytical methods, and institutional commitment to the question has positioned the field for potential breakthroughs that earlier generations could only have imagined. Whether the breakthroughs actually occur depends on details that cannot be predicted, but the conditions for them are in place. The James Webb Space Telescope will continue to characterize the atmospheres of exoplanets in increasing detail. Targets identified during the first years of operation will receive extended follow-up observations. New targets will be added as the catalogue of accessible exoplanets grows. The catalogue of detected molecules will expand, and the statistical power to identify biosignatures will improve. The detection of a definitive biosignature, at confidence levels that would withstand subsequent scrutiny, is genuinely possible within the next decade, though it is not guaranteed. The next generation of large ground-based telescopes will come online during the same period. The extremely large telescope being constructed in Chile, with a primary mirror 39 meters in diameter, will have observational capabilities far beyond any current ground-based facility. The 30-meter telescope, currently in dispute about its construction site, may also enter service. These telescopes will be capable of imaging exoplanets directly, in some cases, rather than relying on indirect transit methods. Direct imaging will allow much more detailed atmospheric analysis and may permit the identification of features that current methods cannot detect. Radio astronomy will continue its expansion through new facilities and improved analytical methods. The Square Kilometre Array, being constructed in parts in Australia and South Africa, will represent a major increase in radio observing capability when complete. The volume of data from existing facilities will continue to grow, and new analytical methods will allow extraction of signals that are not currently detectable in real time. The Vera C. Rubin Observatory, which began full operations in 2025, is producing detections of solar system objects at rates that exceed all previous surveys combined. The detection rate for interstellar objects is expected to increase substantially. Within the next decade, the catalogue of confirmed interstellar visitors to the solar system is likely to grow from the current handful to hundreds or more. Each new detection adds to the sample of material from other star systems available for study. Some of these objects will likely be candidates for closer examination, either through Earth-based observation or through dispatched spacecraft. The institutional infrastructure for studying UAPs will continue to develop. The official disclosure trajectory has not reached its endpoint, and additional information is likely to emerge through continuing congressional hearings, ongoing investigations, and the operation of formally established offices for studying the phenomena. Whether this disclosure will eventually reveal evidence of extraterrestrial origin, evidence of advanced human technology, or evidence of natural phenomena not yet understood remains to be seen. What the next decade might already know, through observations that have been made but not yet fully analysed, through data that exists in archives but has not yet been examined with the right tools, is impossible to determine in advance. The history of the field demonstrates that significant findings can lie buried in data for years before being recognised. The Lorimer burst was in the data for 6 years before anyone noticed it. The "wow" signal was understood only days after it occurred, but never decisively interpreted in the decades since. Anomalous signals are flagged by automatic systems and then archived without full analysis. What is already known, in the sense of being recorded but not yet integrated into the formal understanding of the field, may be substantial. The decade ahead will involve the convergence of all of these developments: telescope capabilities, analytical methods, institutional acknowledgement, accumulating data. The probability that this convergence will produce a definitive resolution of the question of extraterrestrial intelligence is impossible to quantify. The probability that it will produce significant developments, confirmations of biosignatures, identifications of specific UAP origins, resolution of certain anomalous signals is substantially higher. The field is approaching the point where the question of whether we are alone may move from speculation to empirical determination, and the period during which this transition occurs is now upon us. For most of human history, the question of whether we are alone in the universe could not be answered. The instruments did not exist. The methodology was not developed. The institutional and intellectual frameworks for taking the question seriously did not yet exist. The question was posed, considered, debated, but it could not be answered. This is no longer the situation. The question has become answerable, in principle, for the first time. The instruments have been built, the methodology has been refined, the institutional commitment has been established. The data are being collected and analysed at scales that earlier generations could not have imagined. The answer may not arrive in the next year or the next decade, or even in the lifetime of any person now living, but the conditions under which the answer could arrive have been put in place. This represents a transformation whose significance is difficult to fully appreciate from within the moment when it is occurring. For tens of thousands of years, humans have looked at the night sky and wondered whether minds like ours existed in the lights overhead. The question has been asked by every civilization that has ever produced poetry, philosophy, or science. The wonder has been universal across cultures and centuries. The question has been part of the basic intellectual furniture of being human, in the way that questions about death and meaning and purpose have been universal features of human consciousness. What is now occurring is not the dissolution of this wonder. The wonder will persist regardless of what is found, but the conversion of the wondering into an empirical project. We are not asking the question in the abstract any longer. We are conducting the search. We are running the experiments. We are accumulating the data. We are evaluating the candidates. The wondering has become work, and the work is being done by thousands of researchers across dozens of institutions in real time. The evidence that has accumulated so far does not constitute proof. It constitutes the beginning of an answer. The unexplained radio signals, the candidate biosignatures, the interstellar objects, the unexplained aerial phenomena, the structural anomalies that resist natural explanation. Together, these observations do not yet allow confident conclusions. They do establish that the universe contains phenomena that current frameworks cannot fully accommodate, and that the question of extraterrestrial intelligence is empirically engaged in a way it has never been before. What the answer will eventually be cannot be predicted with confidence. The answer might be that intelligent life is common, and that the silence we have observed reflects either deliberate concealment, technological transcendence beyond our detection capabilities, or methodological limitations in our search strategies. The answer might be that intelligent life is rare, and that humanity occupies an unusual place in the galaxy as a relatively isolated example of communicative intelligence. The answer might be that intelligent life is common, but communicating civilizations are short-lived, and that the apparent silence reflects the fact that civilizations approaching our level of development typically destroy themselves before achieving sustained interstellar capability. The answer might be something entirely different from any of these, a category of explanation that we have not yet thought of, that will become obvious only after the data forces us to consider it. Whichever answer eventually emerges, the consequences for human civilization will be significant. If intelligent life is common, our entire conceptual framework for understanding ourselves must be revised to incorporate the existence of other intelligences and the diversity of forms that intelligence can take. If intelligent life is rare, the value and fragility of what humanity represents becomes more acute, and the responsibility to preserve our civilization becomes more pressing. If intelligent life is common but doomed, the question of whether humanity can avoid the same fate becomes the most important question we face. In each case, the answer reshapes the context in which all other human questions are asked. The signals are not silent anymore. The instruments are listening. The evidence is accumulating. The question is being asked in earnest with the tools required to seek genuine answers. We do not yet know what those answers will be, but for the first time in human history, the question has moved from speculation into investigation, and the investigation is underway. Somewhere, in a radio observatory recording data tonight, in the spectroscopic archives of the James Webb Space Telescope, in the ocean sediments containing fragments of interstellar visitors, in the military records of unexplained encounters that have not yet been disclosed, the answer is waiting. Whether it will be found this decade, this century, or further in the future depends on circumstances that cannot be predicted. That it can now be found at all is what is new. The end of the question, the moment when speculation gives way to evidence, has begun. What comes next will determine not what we believe about our place in the universe, but what we know. And the difference between belief and knowledge, in matters this consequential, is the difference between a question that has organized human wondering for tens of thousands of years and an answer that will organize human understanding for everything that comes after.